What is up, everybody? Welcome back to my channel. This is Tony, aka One Leet One Day. If you're new here, this channel does one leet code per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a leet code problem I have never attempted before. You heard that right. There's no prescripted answer here, and we're on the same page here. But don't you worry, I got you covered, and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background. Um, so I'm no better off than most of, if not all of you guys in terms of coding knowledge. But that is okay. If I can do it, you can do it. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking leak codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's coding problem. Um, so this is the situation today, guys. Um, Today I was actually filming this video while um, my desktop decided to throw a tantrum at me and it restarted. So um, at this point in time, I actually think that I have solved the problem, but I haven't submitted it yet. Maybe there's still some bug, but don't worry, I'll still walk you through what I went through to find to reach where I am right now. And then I'm going to submit the code with you guys together to see if it's working and then go from there. So with that being said, let's go into today's problem. Today, we continue on series one, everything about dynamic programming, and the problem is 918 maximum sum circular subarray. So let's get into it. There's some delay here. As you know, I think my desktop is doing something weird today, and maybe it's because it's overheated. I mean, it's really hot here today. Um, and also something's uh, something's not right with my computer. But we'll get through this, and this evening I'll check if I need to, do like a cleaning on my desktop. Maybe there's too much dust, causes overheat, maybe. Um, so now, anyway, we're looking at this problem. Um, 918 maximum sum circular subarray. So let's read it together. Given a circular integer array nums of length n, return the maximum possible sum of a non-empty subarray of nums. So it's similar to the previous maximum subarray. Difference is that it's a circular array. Uh, okay, next, a circular array, what it means is that the end of the array connects to the beginning of the array. That makes sense. Formally, the next element of that of nums I is nums I plus 1 mod n. Yeah, it makes sense to use mod. And the previous element of nums I is nums I minus 1 plus n mod n. Okay, that's pretty neat. You have some generalized expression for that. Okay, and next, a subarray may only include each element of the fixed buffer nums at most once. This makes sense, right? Because you don't want to bite your own tail, or um, or just repeat the loop and find visit one number more than once. You don't want to do that. So formally, for subarray nums I all the way to nums j, there does not exist k1 and k2 where k1 mod n equals to k2 mod n. Okay, so it's like a formal way of expressing that, but we got the essence. You just don't want to repeat any numbers. Right, we have some example here. Let's take a look. Nums equal to 1 minus 2, 3 minus 2, and the output is 3. Because, yeah, because if you take a negative value, you're definitely going to the depreciating value, or you're going to take a loss. So because now we don't have the constraint that you have to start from the beginning or start from the end, as we actually we're trying to do in the classical maximum subarray problem, You can start anywhere, so why not start from the maximum, right? So something like that. Uh, this seems to be the case. In example 2, we have 5 minus 3, 5. Previously, we would just take a 5 here, but now since it's a loop, we can now just go across the border and start from the beginning again. So the maximum is 5 plus 5, it's going to be 10. Exactly, makes sense. And here when we have all negative values and we have to at least, since we have to at least take 1, we just take -2, so we output -2. That also makes sense. Also have some constraints here, number of lengths. The length of the nums is between 1 and 30,000, and the value is between -30,000 plus 30,000. Okay, so that is the problem. And like I said, at this point, actually, I think I have found a solution, but since I lost the video recording, I'm just going to quickly walk you through uh, the steps that I went through to find the current solution that I have. So let me bring you to the first drawing that I had. So um, I took the first example here, 1 minus 2, 3 minus 2, into my sketchboard and tried to find some intuition that can connect this current problem to the previous max subarray problem that is like only a linear list of numbers. Now we have a loop or a circular list of numbers, right? So here's my thinking process. Um, First, I came to the realization that for an efficient algorithm to work for this circular problem, the start point has to be irrelevant. Um, so we don't want to, try some value on that loop and then, move to the next value and start over the algorithm all over again. Because then if we do a full rotation that is already like n rotations, and in each rotation we'll probably at least have to perform n steps. So that would make our total time complexity to O n squared, and that is really bad for a problem with a list of n numbers. If you ever reach time complexity of O n squared, it's probably not the best thing to do. You probably exceed the LeetCode time limit. So I was try to bring the problem down to one of to a subproblem that can be solved using the previous linear maximum subarray solution, which is the Kadani's algorithm, which had a time complexity of O of n, and then a space complexity of O of 1. So it was really efficient. So if we could reuse that, that'll be great. So that was my thinking. And so how do we do it, right? Well, I was trying, I was kind of experimenting this. I look at the example, and I was thinking, um, since the place where we start, like the start point has to be relevant, we can just start from any point, right? So I was thinking, okay, maybe if I just start from the first point, then since like the Kadani's algorithm was something like um, analogous to like a snake or a lizard, like crawling through the list and then trying to grow as large as possible in terms of the sum of the value in the entire snake's body. So I was saying, okay, maybe we can just follow the same intuition, but now since we don't have like a sense of direction, a certain direction to go, which was the case in the maximum subarray original problem. So in the original problem, we were able to start, just from the last element and then moving backward. So our snake was crawling just backward. It's crawling in one directions, right? But now in the circular problem, we just simply don't know which direction we should crawl um, because we will find out that um, that that depending on which direction you crawl, you may end up with different solutions, right? So that is kind of like my intuition. Maybe we need to actually start from both directions. That's what I did. So um, previously we had this intuition like, okay, if we ever if we ever get to a so-called um, um, mm, large negative value or uh, malignant negative value, uh, which is a negative value that is going to ruin all the previous gains that we got um, on our on our like subarray that we have grown so far, then then we're gonna have to ditch all the elements and then just jump to the next one to hope for a new start. So that was that. Like so, once we hit like a malignant negative value, we're gonna have to ditch everything we've gained so far and then jump to the next. And I was thinking, hey, maybe because now we're traveling in two directions, it's like a two-headed snake. And then once we encounter some kind of like negative uh, malignant solutions, malignant negative values, we're gonna just cut that off, and then we're gonna split into two snakes, right? Because previously, because our snake was only traveling in one direction, we only need to cut our tail and just uh, build from the scratch up, and start our baby snake from the next value onward. Um, but since now we're traveling in two directions, it's more like a two-headed snake. And then once we found like uh, a case of this malignant negative value, we just have to split that snake into a two-headed snake. And then we continue moving on with those two snakes. And then eventually, maybe those two snakes, one of them will grow large enough, or they may actually both grow and then they merge together. And then that is going to be our answer. So I was going down that route, but then um, I realized that this this original intuition of like developing a two-headed snake and then cut itself at those ma- uh, malignant negative values was actually a wrong way to perceive the answer. And here's why. Let me show you with this example here. So for example, um, if we have uh, if we have like a list of numbers like this, right? We have some numbers and then we have a really big, really good positive number 1000, and we have a minus 3 and then followed by another 1000 and then followed by a minus 1 and then followed by another negative 9999 and then more values down the line. So if we have a list like this, um, one would think, right? Um, so so negative numbers shall be bad, right? So, for example, you can just ditch this number here, and then uh, you can cut this circular problem into like a linear problem by ditching this negative number. But that is really bad in this case because now this minus 3 is surrounded by two very big positive numbers. We would rather keep the whole package of 1000 minus 3 1000 because this is going to be like a really large sum. But if we cut it into halves, um, we can only take one of those because there's a very negative value on the right hand side that stops us from taking this 1000. So yeah, this is just an observation realizing that you don't want to just throw away any negative number uh, in your first step, thinking that throwing a large negative number is okay. It's definitely not okay. All right. And then yeah, so what I was saying is that I was trying to break this problem down into a subproblem that can be solved using the previous maximum subarray problem. So this is an action that I tried, right? So I tried starting again from the last element, and then start like the judging process of whether this element is like a malignant negative value. Um, so if it is like a, so first if it's like a negative value, um, then we just ditch it. Like we're just gonna cut it. Then yeah, it's like that. We're just gonna cut it here. Um, right. What, are we using pen? Let's actually just use the pencil. Yeah. Yeah, we're gonna just cut it. However, it's not the best thing to do. Let's well increase the length a little bit. Yeah. So let me get a purple. So for example, if you cut that, right? Actually orange. Right. If we just cut that value like we cut this value here, um, or cut the last value there, a negative value there, and then we just use the rest of the list as a classical maximum subarray problem. Um, you know, for face value, it seems to work, but then I realized that uh, there's no justification. There's no justification for removing, any negative value in the context of the ring problem. Because of what I just said, like you think a negative value is not worth it. It's like this expendable. It definitely won't be inside our maximum, our optimal max subarray, and you can just throw it away. No, you cannot justify it. I even tried justifying throwing some, like popping some negative value array away so that we can break this down into a linear classical maximum subarray problem by following this logic. Um, so this logic, what it is that we're trying to you know travel from the last element in the list backward, and then find our first ditchable or expendable um, mag malignant negative value. So it's not like just any negative value, first negative value we found. The negative value has to be bad enough that it's going to destroy the previous streak of subarrays that's been accumulated. You would think that if we can verify that, then that negative value is bad enough that we can justify ditching it. All right, that would be good because if we can justify ditching like a very bad negative value, then then we can effectively reduce this circular max subarray problem into the linear max subarray problem. That sounds great, right? Like it all sounds perfect. But in the end, I realized that I cannot justify that, and I'll explain why. So this goes to the second page that I created. So So, in this second version of thinking, because because I realized that I really can't justify popping out any value uh, um, as like an expendable negative value, uh, I decided, okay, why don't we just complete the logic loop and do build two cases. Case one is that we do pop something, right? We do pop a negative value. Uh, and then we solve the remaining classical subarray problem. Or um, what if we can't pop it, meaning that the value that we just popped is actually part of the solution array, the maximum subarray. So we're gonna have to explicitly look into that and find what's the maximum if that's the case. And then we need to compare case one and case two, and that would be that would complete the logic loop, and that will give us the maximum that we wanted, right? So this is actually a more mature, and I hope it is a working logic. and and the biggest takeaway is this one, right? We just demonstrated from the previous slide that you cannot rule out any negative value in the first step that you tried, right? In the first step, because you never know. Like a negative value, if it's surrounded by some very good positive values, no matter how negative you think that negative value is, and no matter how bad you think it is. You cannot just, put a death sentence to it and say it's so bad, I'm just gonna ditch it. I'm just gonna pop it, and I'll work with the rest of the array and reduce that into a classical maximum subarray problem. You don't do that because I failed to justify that. So, um, but it's not like an effort in vain, because I realized that there's really good value, or there's really good motivation to actually pop something, because once you pop one value out of that array, you effectively broke the chain, broke the circle, and you are left with a linear maximum subarray problem. So we really want to um, to actually have this case where we pop something. But in order to patch the logical loop to justify this pop, we need to prove that the counter case, which is the case where we absolutely need that value, and we can't pop it. Like, what does that mean? That means like the popped value should be in the solution array. So if that is the case, we have to prove that, um, we basically need to work with both cases and find the maximum subarray that we can find in both cases, and then find the maximum between those two maxes, and then that will be eventually our maximum. Then we can justify the whole thinking. So right, I think I just walked ourselves through the thought process, and down to the implementation. I had a little bit of a personal touch in it. So um, let's say our array, original array, starts from index 0 and ends with index m minus 1, and it travels in this kind of like clockwise fashion, right? Um, Starts from here and then travels all the way down to the m minus 1, and it stops. Um, so so um, uh, so when I was trying to work out the case one, I didn't want to just pop any random number, because popping out a positive number is not making any sense. We don't really want to do that, because any optimal solution will not involve, like, I mean, it's just not right to pop out a positive number, because we want to take as many positive numbers as possible, so we don't want to waste any of them. So I put some personal touch in it, and I basically said that we're going to find the first negative value that we can find by just traveling, starting from a position, and then traveling down that position. Once we find a negative value, we start to split that into two cases. Case one is we actually pop that negative value. Case two is that the optimal subarray actually contains that negative value, and then we're going to continue our discussion in both cases, and then come out with the maximum sum of the subarray that we can find in either of those two cases, and then we're going to combine them, find the maximum of that. So that's what I did. So in the first case where we actually pop, that is a very simple. We can reuse the code from yesterday's maximum subarray and use that with a modified array that just pop that negative value out. In the second case, where we actually have to contain the negative value in our maximum subarray, uh, we we basically have that knowledge that this negative value uh, is definitely in the solution. So that's some certainty right there. And we can still reuse that snake or crawling intuition to find the largest possible sum that we can find, uh, with the condition that the array, the maximal subarray contains this negative value. So what we do, we start from that negative value index, and we travel in both directions, both counterclockwise and clockwise. Um, and then we continue traveling until we hit a stop. And what do I mean by hitting a stop? A stop is defined by, finding a malignant negative value in the classical maximum subarray sense, which the negative value, it completely ruins all the previous gained like momentum, or like the previous streak of positive sum that we have gained so far, or sum, not positive, sorry, it could be negative. Like the negative value completely ruined the value, the current max, the current gain that we have, that we have achieved. So when that happens, that is a hard stop, because traveling further is meaningless, because we know that we have to include this um, this like it's almost like an anchor point. We have to start from this anchor point. Uh, and if we have encountered like a malignant negative value, then we either have to cut ourselves and start fresh uh, over the next value, or we basically stop there, right? Because containing a malignant negative value is definitely not the way to achieve an optimal subarray. So, but since we have to contain this anchor point, so we don't really go over it. We just stop right there. Uh, and then we're gonna our um, remember our, let's say, what is it? Our we're gonna remember our current max in this direction, right? And we're gonna call it current max backward, because let's say BK backward, because yeah, we're gonna memorize the best subarray sum that we have achieved so far before hitting that stop, and then we're gonna do the same in the clockwise direction, and we're gonna keep traveling until we hit a stop here, and we're gonna take the current max of that forward attempt, and then basically, yeah, that's going to be the gain that we have achieved by exploring this much until the hard stop, and then we have achieved this current max forward, and then we combine them, and then we find the maximum. Oh, well, sorry. We actually sum it up, right? We actually sum it up, and that is going to be the sum of the second case, the sum of the second case. Yep. So and then we just used the existing code for the classical maximum sub array for the first case, and then we're gonna these two cases, compare these two cases to reach our final maximum. So yeah, that's the whole structure, the whole workflow of this uh, approach that I proposed. And let's take a look at the code that I developed so far. Uh, we may still have some error in there, and I just think I realized something was wrong. So let me just walk you through what I had, and then I'll work on fixing what I thought was wrong. So we have built this main function here, max subarray sum circular, and what we're doing is that we first have a while loop, uh, to find a first negative value if possible, and then that's where we're gonna start popping or not popping. So this is like finding that k here. Um, and just by convention, we would like to start from the last index uh, in the original nums list. Excuse me. And then I'm going to use a while loop to decrease k by 1 each time, and then just to check if that nums k is negative. And once we found the first negative value, we're going to break, and we're going to record that first found negative value as int first neg, right? Uh, but if there's like absolutely no absolute value in the array, in the list, in the original list at all, we're going to hit the end of the while loop with a k value of -1, because the last k ever that we can find in the list is 0. And then because we're gonna perform this k minus 1 action at the end, so if we have like all positive values in the nums array at the end of that while loop, we're gonna have k equals to -1. So if that's the case, if k equals to -1, we're just going to return the sum of the original array because everything is positive. So we're justified to return that as our maximum sum. Uh, otherwise, we have obtained our k, which is a negative value, first found negative value. Then we're going to start splitting it into two cases, right? The first case is where we actually pop the k out, as we indicated here. We pop it, and then we're going to solve the remaining classical subarray problem, right? And then the second case is uh, where the optimal subarray actually contains the number k. Uh, so we're going to use a function to solve that problem explicitly. And we decide to deal with the second case, because if we actually pop that using this pop function, it's going to affect the original nums array. So we want to do that later before case two. And then eventually we're going to return the maximum between both cases as our final answer to the original problem. So and of course, in case one, where we have popped one index out and deal with the remainder, we just need to call like the existing solution that we had from yesterday's original max subarray problem, which is down here. Uh, we had so basically this is our own implementation rediscovery of the Kadani's algorithm. We're gonna just use it fine, but um, but I think we need to modify it because the new constraint is different. Now the new constraint is like, okay, we can go as negative as minus 30,000 or as positive as 30,000. So we need to change that. We need to change that value here as well to make sure we cover the new constraints. Yes, and let me walk you through the function that I built for the special second case where the optimal subarray contains nums k. So as we explained before with our diagram, if that's the case, we're going to solve the circular max subarray problem with the given knowledge that k is in the max subarray, right? Um, and we want to travel both directions from k and stop at the first, at the first malignant negative values. Uh, and if there's no malignant negative values on either side, then we're going to return the sum of the whole sum list, no whole nums list. And although we said we're going to travel both directions, we're going to have to, because we're not doing parallel computing, we're going to pick one to start with, and I chose to pick the backwards direction or counterclockwise direction to start first. As we can see here, like we just found the k, and then we're just going to travel counterclockwise first until we hit a stop. So that's the first thing I'm doing. I just made an example here. For example, how am I going to do that? So, for example, the k that we found as a negative value is 2, right? I mean, k is 2. Well, it's a negative 2, right? Because it's a negative value. Um, right. If we found our k equal to 2, then what I do is that I just split right after that negative value, and then wait. Uh, oh, sorry. I think there's a It's actually we actually first travel forward. The way I wrote the code, it wasn't like traveling backward first. It's actually traveling forward first. So I'm gonna update that documentation here. So actually, we start from traveling forward, and what that means is that I split right after the negative value that we found, and then we have two parts, right? And then we're gonna swap them, and it becomes this new array. The reason why we want to swap them is because now, uh, uh, um, let's say, because we're going forward, and uh, when we're going forward, right, we're gonna treat the k as like the starting point, yeah, and then we're gonna go forward like that. Um, so we want to let's see, huh? I'm looking at it, some inconsistency here. So -2 is where we're split, and if we want to travel forward, maybe that means we need to yeah, start with -2 and then travel in forward direction. So it should be -2, 3, 4, 0, 1. Right? Right. Yeah. So that this is somehow wrong. It's inconsistent, but I'll fix it. I'll fix it. Let me get back to first. Yeah. So I was saying that I found something that was probably wrong in this current implementation. Is that instead of doing sum, I was doing a max. So yeah, it shouldn't be a max. It should be a sum here. I'll just put a note here. So just telling me that instead of a max, I really should use a sum here. Uh, don't use max, use sum. Right, this is something I need to fix. So there are two things that we need to fix. The first thing I need to fix is to fix the order of things because we said we're first going to travel forward. So when we say we travel forward, actually, according to this diagram here, it means we need to, yeah, we need to build an array. Um, right, we need to build an array that actually starts from this k and then goes forward, right? But because previously when we were doing such things using the max sub array, we were doing backwards. We were starting from um, n minus one, the last value, and then going backwards. So in order to reuse most of these code here, right, I'm going to actually flip it because it's a sub problem anyway. I mean, it's a sub problem, so we can manipulate the order of the nums array to fit the structure of the sub problem, as long as in the end we're solving the same thing. So now what we're actually going to do is this. Uh, because we're actually going to search like in this way, right? Like -2, 3, 4, 0, 1. Uh, but because but actually we need to build that thing in a backward order, right? So that it fits the our previous code. Uh, I'm going to actually put -2 at the last, and then the second last is 3, and then the next one is 4. So it's going to be like this: -2, 4, 3, and 0 and 1, right? So that's the new array. So how do we do that? Well, we're going to basically initialize that array with the right number of elements, and then I see that we need to actually just flip them. Uh, mm, First split them, and then just flip them within themselves, and that would be good enough. So how do we do that? Well, we are going to say the first part is where we from 0 to m minus k minus 1. Well, here k is 2. This is actually 0, 1, so it's 0 all the way until 2. So it's 5 minus 2 minus 1. Yeah, so yeah, I think that makes sense. M minus k, and well, actually no, this should be n all the way up to k. That's it. Um, and then it'll be the same thing, but it'll be k to from k minus 1 all the way to minus 1 uh, with an increment of -1, right? Or actually, if you just want to go to the beginning, you can just say empty, and it'll go to the beginning. Yeah, yep. And then the second part is uh, from K onward, right? From K onward, uh, and it's from K to the last one, right? Yep. Um, and so mm, we can do that. We can or we can just be explicit and say that it's gonna be the same numbers but in a flipped way. So it'll be the first one is n minus 1, and then the last one is gonna be k minus 1, and the increment is minus 1. Yeah, so this is how we do it in a forward way, right? And then we're gonna call this function to reuse our previous code, a modified version of the previous code to stop until to stop at the first malignant negative value, to stop at the first malignant negative value, and then return uh, the current max uh, of the subarray found that contains this k here. And then, excuse me, and then we're gonna go in the other direction, going backward, which is travel. Still start from this anchor point because we have to include this point. Travel backward, and then and then all the way to where um, travel. Yeah, we can. So we're gonna build the array. We're gonna build the array still starting from -2 as the last element, but since we're traveling backwards, meaning we start from -2 and then we go to 1 and we go to 0, something like that. Therefore, we want our array to go like so this is going to be the last value we ever wanted, right? And because we're traveling backwards, I think we're going to still make this kind of split. And then we want to start from 1, right? And then we move on to 0, and then we move on to 4. uh Wait, isn't that the same as this? Because um wait, I think there's something wrong. Let's just try the forward one again. So the forward one, where we go forward, is that we want to build a new array that starts from this and then end there. Right. Uh, so it goes this way, right? So it'll be uh, k and then k plus 1, k plus 2, something like that. But then in the end, we'll have to reverse it. So it'll be actually the first element is actually k minus 1, and then k minus 2, and then all the way to k. So k minus 1, k minus 2, k minus 1, right? K minus 2, and then all the way uh, uh, 4, all the way back to k. Yeah, that makes sense. So that was the flip, yeah. But what about this? If we're going forward, if we're going backward, so now if we're actually going backward, so this is this point is going to be our starting point, and we're going backwards. So this is going to be k minus 1, k minus 2, all the way till k plus 1. But then since we're doing it backwards, so the first element in the array would be k plus 1, and then k plus 2, and then all the way till k minus 1. So k plus 1, k plus 1. Okay, so that's how we split. We start from k plus 1, which is 3, and then k plus 4, k plus 2, and all the way over to the beginning and then to, this value here. Right, so this is going to be the new way to split it. 0, 1, 2. Okay, so let's see how we do it. So this k is still 2, right? So for the new array, um, from, let's say, k plus 1 onward to the end, so to n minus 1, explicitly, this will become nums array, the original array, starting from, oh wait, sorry, and 0, actually this is 0, and then 0 all the way to what? To m minus 1, m minus k, m minus k. So how many elements are there? We have m minus k elements there. But to represent it in this format, um, we have to make sure that the second input is mm, so for example, this is going to be 0 to 1, and n minus k is going to be 5 minus 2 is going to be 3. So it's going to be actually 0 to 3, so it's going to be 0, 1, 2. That's not right. We need to put a minus 1 to make it right. So this will actually be 0 all the way to 0 colon 2. So it'll be 0 and 1. Yeah, that's how it makes sense. And this one will be from nums k plus 1 onward to the last element, to the end of it. Yeah, excuse me. Yep. And then for the remainder, which is um, index m minus k minus, wait, uh, hold on. Um, right, m minus k minus 1 from this onward. So from, this is like m minus 1 minus k minus, this is 2. From 2 onward, all the way till the end, right? It should be the original nums list from 0 um, all the way to k, looks like it, because this is like k plus 1 elements, and this is also k plus 1 elements. That sounds about right. And then we're going to build it, and we're going to solve it. So anyways, I think we just built that list all right. But then we need to fix another problem, which is this. We were using max where we actually need to use a sum. So why do we need to use a sum? Because we have traveled both ways. Um, but then we stopped at here for the backward direction, and we stopped here at the forward direction. So um, the maximum sum, it should be combining both of them, right? And then because we recalculated this k value twice, we need to take one out of it, and then we right. Uh, yeah. So this is one little detail there. Uh, remove the excess nums k that was calculated twice in the first place, right? So we need to have that little detail there. Remove the excess um, of that, right? Sum, and then remove the excess, and then it'll be the maximum for the second case. So let's do that. So instead of using return max of that, we need to use sum. So we need to sum this, and then we need to remove that excess excess remove that excess k from it. Yep. Because this has a negative value, by removing that, we actually are adding some value to it, which is great. Yeah. Now, now let's see. Now let's see what exactly we're doing here. So for the first stop, what we're doing is that yeah, we're going to now look at how we implement this sub problem of traveling in one direction until we meet a stop. And we basically uh, took the code from this max stub array problem and just repurposed it for that. So let's read the description that I wrote earlier. Start from the last element in the nums list, right? That is the previous nums k, a negative value, and build the subarray from there backwards until we find a first malignant negative value that cancels out all current gains. And once we found that point, we're going to return the current max right before hitting the first malignant negative value. Right. And if no malignant negative value is found throughout, we just return uh, uh, um, the current max. Right. 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 But I think there's still like a flaw here now that I'm reading it, because when we're traveling like in both directions, we don't want to overlap, right? If we're overlapping, that is pretty bad, right? Right, we don't want to overlap. So how do we do that? Um, so at the end, so there are possibly two things that we need to check here. Um, yeah, there are probably two things that we need to check there. This is number one. But the number two thing that we need to check is that check if the two um, current max, check if the two current max had an overlap in elements, because that's the last thing we want, right? Like we went all the way we want here, and we found that we're overlapping, because overlapping is not allowed. So how do we do that? Um, so when we store our current max, we definitely want to store its index, right? Current max, and we want to store the index, and we want to check that the index for the current max of the backward action and the current max for the index for the current max for the forward action, they don't overlap. So I'm going to use yellow to indicate that. So for example, this is the index of our current max, current max current max backward, right? This is like the head of it, right? And then if we actually found our current max here in the forward action, this is going to be uh, right uh, uh, cur max forward, forward head. Then we're basically gonna compare this backward head and the forward head to see if there's an overlap. So in the case of an overlap, yeah, let's see, what do we do in case of an overlap? In the case of an overlap, that means we have basically just the entire traveled through the entire grid, the entire list, and we should include every element in the list as our return value, right? And if that's the case, and we're gonna do something at the proper level in our function, meaning that in this maximum sub case too, we're gonna build the case, check if the two uh, check if the forward and backward indices overlapped. If so, just return the sum of the original nums, right? Um, so the original nums, mm, but that is contradicting because we're including a negative value and we're returning the whole thing. Then why don't we just pop out the negative value, right? Yeah, this is kind of contradicting because if they actually overlap, if they actually overlap, then then that means, right, if they actually overlap, that means we don't hit any stop signs, and then these two this kind of like the two-headed snake, it meets each other um, face to face, and then merge together, kind of like that. But that actually defeats our assumption in case 2, where the solution array includes the popped value, because there's an inherent assumption here, because if it's a negative value and we have included that negative value inherently in our optimal subarray, that means the solution cannot be a full list, right? Right. So yeah, I think we don't have to do that because yeah, it's impossible, right? We don't need to do that. We don't need to check this. But it's good to, ask this question, right? Because this is ruled out by initial assumption of case 2. Case 2. Yeah, maybe we should, use A and B labels here, just not to conflict with the 1 and 2 above. Right, right. So we don't really need to do that. So all these concerns that we have in the yellow color is basically just over worrying. But it's good to over worry or question about something. But we found out that it's actually not the case. We don't need to worry about it. That's totally fine. So come on, we're gonna just remove that little yellow marker. How do we remove that? Well, let's just remove that yellow marker, yellow marker, yellow marker, and everything here. So we don't need to worry about it, okay? It's good that we thought of it, but we just proved that we don't need to worry about it. Okay, we actually we actually don't need to check this. You know, uh, this is like a no because we actually don't do it. Okay. Um, so that means our code is still all right, and we just need to make sure that we're going to remove the excess nums k that was calculated twice, and then we're going to just sum it up, right? Yeah, we're going to sum it up, and then we remove the excess nums k that was calculated twice. So sum of that minus num k. Yep. I think we have potentially the answer. Whoops. But int object is not iterable. What does that mean? Uh, what does that mean? Int object is not iterable. Are we iterating it? I don't know if we're iterating anything that's like that. Um, some okay, so maybe ah yeah, maybe we don't need to use that glorified sum function. We just need to add it, right? Yeah, that's really what we mean. Add them both and then just minus that. Let's try it. Um, right, so it looks like we passed all the test cases. So let's send this thing to our lead code to see if it works. But the code, I mean, I have a little complaint here, which is like the code is pretty long because we were relying on previous solutions and that made this code actually super long. It's got, well, 150 lines, but hopefully, no, it doesn't work. Okay, so there's a none type in there. There's some bug that we need to fix. Um, let's hope it's not a bug uh, in the algorithm itself, but it's just some implementation bug, right? So what do we expect to get from here? We're expecting 8, I believe. Oh, sorry. I think we're expecting an answer of 8, but let's just see what is the error that we're seeing online. In max case 2, first up, if current max is greater than global max, is not supported between instances of none type and int. So our current max is a none type for some reason. All right, let's start debugging. Yeah, the computer is super slow right now. I think there's something wrong with my CPU or hardware. Right, let's restart our kernel, clear it, and then we're gonna put our debugger on and set our breakpoint right at that index 87, right? I think it was at 87, yeah. So we're gonna run that and we're gonna wait until here. So yeah, current max is none type. Why is that? I believe it is because the nums contains a none type. That's what I thought. And exactly. So the problem was upstream when we were first calling, or maybe calling the nums array. So let's see what is the nums array. It's -5 none type none type, and the k is 2. Well, k is 2. That's weird because k should be 0. Like, why is k 2? Yeah, it's kind of weird. Um, because we need to be pointing at the negative value there. So anyway, that means maybe our previous fix to this uh, num's new calculation had a problem, had an error in it. So um, anyways, we're gonna restart our kernel and we're gonna put a debugger right before the calculation of the num's new array and find out where the problem is. Put debugger on. Yeah, it's just reacting very slow right now. I'm gonna put the breakpoint at line 48 and then start the calculation. So now we have our nums array as, it's so slow, -5, 3, and 5, right? And what is the k here? K is 0, which is correct because the first value is the negative value that we found. So what we're doing here is that we're going to, in this way, uh, um, it's going to be right, -5, -5, 3, and 5. So we're going to first just initialize the um, nums new as a list of three non-values, two non-values. Why? N minus one. So n is what? N is three, right? Whoa, wait. Uh, yeah. Why is this like n minus one? I think this should be n. Right, this should be n. So we're going to change that because I think that was wrong. Um, this should be n elements, right? So we rerun it. Same problem. Yeah, but then we're gonna probably still have to restart the kernel. Put on the debugger and uh, put a break sign, put a breakpoint right there at line 48, and then run it. Right. So let's see. Our k is equal to 0, which makes sense. The first element is a negative, and then our nums list is the original nums list minus 535. Okay, that's one step forward. Um, Now we have a nums new list as three non-type. Yep, that's correct. Um, so the first step, let's see what the first step does. This first step, what it did is, let's see. Wow, that is so wrong. That is so wrong. Now we have six elements. Whoa, that is so wrong. So k, again, let's see what is the problem. So 0 to 0. Right, 0 to 0. And that doesn't really make sense, right? 0, right? If it's actually 0, then 0 to 0, I don't know what will do. What will that do? But it's wrong. Definitely, we're going to fix that. Let's stop it right there, and then we're gonna stop the debugger, and let's just say we're gonna copy this test case, right? And say now our test array is like this, and our k is rightfully 0, and now this has to be n, right? And what is our expression here? Our expression is like this. Mm, Update that. Whoops. We're gonna, what? How do we, yeah, just indent and then try to do that. Probably it'll give us some error. Oh, okay, it's giving us none, none, none. Right, that's so wrong. How about just hide the last step? Let's see what it gives us. Whoa. Yeah, it's more nuns. Uh, so 0 to k. So 0 to k, what is like 0 to k? 0 to 0 equals to, let's see exactly what this is. Okay. From k minus 1. So k, if k is 0, k minus 1 is going to be uh, 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 minus minus 1. And then uh, 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 and then all the way to the beginning. Right, so this could be a problem. Because if this is the case, and what we really want it, yeah, we want what? We want, because it's -5, and we want it to travel forward, and then the way we travel forward clockwise, then what we wanted is to have like an array nums new in the shape of -5 as the last element, and then 3 as the second last, and then 5, right? Travel forward. This is what travel forward. For the travel forward case. Yeah. Uh, so that's what we wanted. Um, we actually kind of like, I don't know, got it? Is it like, no, we didn't. Um, so actually what we're trying to do is we're trying to start from here, right? We're trying to start from here. No, we're trying to end there. Uh, we're trying to, you know, start from this negative value and go forward like that and like that. But we in order to reuse the code we had, we actually need to, reverse this list. That's what we're doing. Yeah. So why don't we make it simple, right? Like why don't we before we reverse the list, let's just make the positive direction list. For example, we're already there. I mean, we're already there, right? We're already there, and we're just gonna reverse it. And let's just see. Right. I think that's the right way to do it. If this is that and k equal to 2, if that's the case and k equal to 2, uh, if we go forward, then we want we want it to be like this, right? And then we want it to be like this, right? We just do one step at a time, and then we want to reverse the list, right? We can just do it uh, using the same variable so that we don't really need to occupy one more memory location. 1, 0, 4, 3, -2. Yeah. So if we want to end up doing this in a sequential way, of course we can initialize it, and then what we do is that we can count. Right, we just count down, right? Like, come on, we don't have to do that. I mean, we can just count from our kth element onward, right? And then um, in an ascending order, and then all the way to what, k minus 1, right? Because I think that is going to work. What? No, it didn't. Okay, right. So all the way to the end. What about that? Yeah. Uh, yeah. Just like that. Well, um, plus. Yeah, maybe we can use the plus thing. Nums. Um, whatever first element all the way to k minus 1 with the stride of 1, -2, 3, 4, 0. uh oh, okay, actually to k, right? So we actually have that. So then we actually don't need to initialize something like that anymore. It just, yeah, it's just like that, right? um and then we want to reverse it. So nums new equals to nums new, let's say last element down to the first element with the stride of -1. So we reversed it. Yeah. So actually, this is much cleaner than what we had before. I'm gonna use that. Uh, right, because this is much cleaner than what we did. And if we apply it to now the problem of what 5, this problem of let's say -5, 3, 5, -5, 3, 3, 5, and if our k is 0 because that's where our negative index is, then we're expecting something like 5, 3, -5. Yep, that's right. Yep. And then what about the second one where we want, the new nums array like that? So if this is the behavior that we want, right? If this is the behavior that we want, let's just work with it. Uh, you know, if this is like the behavior that we want, we have our nums equal to this, right? And our k equals to 2. Um, if you want this, what this basically is, uh, um, this is basically, yeah, I'm just gonna directly write it out. This is basically nums of um, k plus 1 to the end plus nums the beginning all the way to let's do a increment of 1 here. So from the beginning all the way up to k um, with an increment of 1, right? And then we reverse it. Yeah. Do we reverse it? No, we don't even reverse it. So this is it. Come on, be quick. Oh, we need to show it. All right. Nums new. Something's wrong. 3401. We're missing the -2 there. Why is that? Uh, well, why is K not there? Oh, okay. Because for the second element, we always need to give an extra there. So 3401 -2. Yep, that's what we wanted. So very simple. We just have one line there. So this is much more elegant than what we had before. Just one line solves it all. Yep. So now let's try run this and run this test case. Yep, and it has met our expectation. Now let's try all the test cases, and they were working. And let's just submit this code to LeetCode and see what happens. Run code, run examples. Why is it so slow? All right, it worked. Submit the code. Wrong answer. Okay. Let's work on it. Let's work on this new test case and see what went wrong. I mean, I still have hope that, this existing algorithm is almost good enough. Uh, we're expecting 18, but we need to just work out the little details that we're missing, and then we'll be there. Right, expect 18, and we got 14. So let's just take this array uh, and then work it work it here. So for example, this is our array, right? Let's see how we're gonna do how we're gonna perform our calculation here. So we started from the last element, and then we moved forward, moved backward, and we found our first negative value. So this is gonna be our k, to be popped or not to popped. So there are two, right? Like if we pop, we're gonna end up with this 9, 4. Uh, wait, wait. It's not like we pop, right? It's actually when we have to recombine the list instead of popping it, because popping it would mean a complete different array. Right. Yeah, the remaining problem is not a pop. It's not a pop. It's not a pop. It is a reconstruct, right? You know, reconstruct. Yeah. So that is probably a mistake that we found, and it's a pretty critical mistake. So we don't really pop it here. Not pop. Reconstruct nums k and work on the remainder. Um, so how do we reconstruct it? Mm, let's just use a function to define it. Okay, def reconstruct self nums and k and nums, right? It's a function, and then we're gonna use some documentation there, uh, and we're gonna say, hey, reconstruct a new nums array that is a result of removing uh, nums k from nums and start uh, uh, um, yeah, that's it. Like, I mean, you got the point. So it's not like just popping and then merging the rest of it, but it's actually, you know um, let's just experiment with what we should do here. For example, in our test case here, if it's like this, yeah, and then we want to nums is like this. We want to reconstruct nums into because we want to remove the 7, right? Like the k here is equal to 2. Uh, so once we remove that 7 and we reconstruct it, it'll become 9 minus 4, right? 9 9 minus 4. So what we should do is we definitely nums re yeah reconstruct recon right reconstruct. um, it'll be uh, nums k plus 1 all the way till the end with an increment of 1, right? Assuming that we still have some values after it, right? Like that we have if condition. If k is less than length of nums, we better just give a value to that less than n minus 1. That meaning we still have some remainders there. Um, right. Then plus nums. from the first element all the way up to k. Yeah. Else, what do we mean by else? Um, else if like k is exactly the last element, then our nums recon it'll be just this, right? Because there's yeah, just like that. And then we just want to see what is nums recon in the end. 9 minus 4. Yep, so this works. Um, yep, this works. Now I'm just going to take the entirety of this and build it into that function. We have nums, we have k, and we're going to return that, right? Um, so return that. Return type list of nums, right? Yep. And so we're going to actually instead of pop, we're actually going to do self dot reconstruct k nums, right? And that is something we're going to use here, and then we're going to apply max subarray to it. Yep. So I don't know if that fixes the problem, but yep, that actually fixes it. Now let's see. Right. With that fix, we have being able to, solve um, this failed test case. I'll just run the code and see if it passes some of the initial test cases. Okay, we still have a wrong answer. Uh, well, we're just growing, okay? Um, and let's see with this new test case what went wrong. Let's see. What are we expecting? We are expecting 16. Okay. Uh, right. So let's just highlight you and then see what went wrong. Let me actually, you know what? I'd like to see mm, the process of calculating it. What is the maximum sum between each and each? Uh, right, right. Let's see. I mean, we're close, but just not exactly there. Max between max case 1 and max case 2, right? Max case 1 is this. Max case 2 is this. Containing k, and yeah, this reconstruct of k. Mm, let's put a break here. Somewhere like there. Yep. And I just wanted to see, come on. Oh, you only give me that. All right. Let me return a few things. I'm gonna return. If you don't want to do that, let me just return that. Um, and we're gonna return also max case 1. I want to return max case 2. We want to return those three values at the same time, okay? 13, 13 minus 2. So I also want to find, also please give me the k value right there. So the k we found is 7. Does that make sense? 0, 1, 2, 3, 4, 5, 6, 7. Yeah, it does make sense because that's the first negative value that we found. So we're doing all right in finding our k. And then this is the maximum mm, of reconstructing you know the array after removing -2. So it's this. And then so when we're calculating this, what does this give us, right? Let's just go back to this original problem, not jump game, but maximum subarray. Yeah, we're gonna just include that additional test case and see what um, what this would give us. What, 13? Yeah. Let's just try this, okay? Yep, it's 13. So is it really 13? I mean, you see we have a 3 here. The -7 is definitely a bad negative value. It's gonna make 3 so useless. So we skip that. We go to 9. And a -9, these are so useless right now. So we just take 5 and 8. Yeah, so it is indeed 13. Uh, so I'm sure this is actually gonna give us 13. All of this. Uh, oh, but then, if we actually include these, like 3 minus 2, that's gonna give us 1, right? Uh, oh, and if we start from here, right, from here, these are actually gonna be helpful. And then this is 13 on the left hand side, right? And then we're gonna have what a 3 on the right side. So 13 plus 3, that's gonna be 16. Yeah, yeah, right. So if our algorithm actually works, and we have split it, like, yeah, we have split it at the value -2, um, then the optimal value, it should exist. It should exist uh, in the second case where the -2 is actually part of it. Uh, so the way we calculate it, the way we use like the double-headed snake to expand from this um, anchor point, or like a value that we know that must be part of the maximal subarray, is where we now expand in both directions. If we expand in the forward direction, we'll include 5 and 8, and we'll even include this -9 here. And we're actually not going to stop. And right, we're actually not going to stop there. But then, what is like the max, the current max in here? Like the current max is of course 13 because it's 13, and then -9, that would be like 4, and then +9 is that again 13. Uh, yeah, and then -7. That's bad. But it's not so bad. Uh, 13 plus 7, that's going to be 6. 6 plus 3 is going to be 9. So we're going to travel all the way here, right? And then what about traveling in the other direction? So if we travel, uh, uh, if we travel in this backward direction, and we are going to hit a -7, and that is something that we're going to hit, and we're going to stop, call it a stop, because according to our logic, right, we're going to say -7, it's a malignant negative number, so we're stopping here. We're not moving forward anymore. So in the end, We're gonna take this for the backward expansion or exploration. We're gonna stop here. For the rightward expansion, we're gonna stop. We're not stopping here. We're not stopping here. We're not stopping here. Uh, we're not even stopping there. So we actually could cause like a biting our own tail kind of like a situation, and overall this idea of using a two-headed snake to expand, that failed, right? Like I mean, the overall idea of splitting into two cases, that is still fine, um, but it's just like this heuristic of trying to um, stretch in both ways and then stop until we hit like a malignant uh, negative number. This heuristic or this idea, this intuition actually failed. Mm. Why? We have seen that here the actual best thing to do is to do like this on the left side of the -2 and then this on the right side of the -2. Right, so just to give you an idea what you should be looking for. But how? I mean, how are we going to identify that? Let me just take this case very seriously, and then we're going to reconstruct. We're going to reconsider. No, we're going to reconsider our approach. We're going to reconsider our approach seriously to make sure that we are dealing with this case. Right. So black, and we are going to first just draw a circle, okay, to represent our case. And we start here, and our n equal to 0 is here. This is our last value, right? It's n minus 1. So this is 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 elements. I'm going to draw it like 0, so 4 on each side, right? 0, so it's 0, right? 5, 8, minus 9, 9, minus 7, a 3, and a minus 2. Yeah, so that's what it is. That's what it is, and let's just deal with it. Like we were trying to follow our previous approach. See if I can still make it work. Right. We're gonna use these colors. Right. Let's use orange. Uh, 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 well, let's use black a little bit. Right. Um, so we first found our first negative value. This is found to be this. Right. This is gonna be our k. Our k is gonna be n minus 1. Right. So this is our k. Uh, our k here. And then we're going to work on two cases, right? So there's the case 1, which is like reconstruct, which we already worked out, like the maximum is like 13, it's suboptimal. And case 2 is now we are going to start with this, we have this, mm, it's almost like we need to always include, include -2 in, optimal array. And is that still true? Like, I mean, in fact, The optimal array, of course, it includes -2 as part of it. So we just need to find it, right? Uh, so the answer that we're looking for actually is this, right? This is like, yeah, this is like the answer that we're looking for. And we need to basically come up with a new algorithm or modify or fix our previous algorithm to make sure that we can reach this correct answer here. Let's see if we can do it. Um, I mean, our previous logic didn't work because if we just stop at uh, uh, um, the first, if we just stop at the first malignant negative number, for example, in this case, we're going to just stop here. Uh, uh, and and in this direction, we actually accumulated like 13. So we're actually not going to stop here. We're adding more positive values, and but this -7 is tolerable. So we're just traveling all the way until until we get until we got here, and so we're just basically, yeah, and this is already like an overlap. Like we have our first array traveling uh, this long, right? And then our second array actually travels this long. So they definitely have an overlap. And that is the wrong heuristic to use. So how can we come up with the heuristic that includes this point and then end up at this right answer? I mean, um, because again, this is no longer a classical max sum array problem. It's a new problem. It's a ring. So actually, if we just use the exhaustive search, right, we can have how many values out there? In one direction, it's n values, and then um, and in the other direction, we could do the rest. Uh, uh, so it's almost like an ON2 if we do an exhaustive search just to include, just to calculate the maximum possible subarray, including -2 here. So that's definitely not a way to go. It's too dumb. We definitely need some smarter approach. Let's rethink about the snake analogy. Mm, See if we can come up with a smart snake that always keeps its body here, right? So the snake, it always is going to keep its body around the value 2 here, and then it may grow, in this direction, or it may grow in this direction to include as many number as it wants. But the end goal is that the snake wants to be greedy and it wants to, uh, you know, eat up as many positive number as possible and avoid as many negative numbers as possible. So maximum growth. So let's just actually start with that, right? So first we travel to 3. That's definitely a yes. And we travel to 10 and 5 and 8. Oh, 0 and 5 and 8. That's a definitely yes, right? So these are like money in the bank, right? So we're going to call it money in the bank. They're just going to take, right? You just need to cash it. So then when it comes to these ones, those are the hard decisions, that you need to make. Do I take this or do I take this? I mean, the remaining good stuff is this like number 9 here. Uh, but then you have a -7 and -9 in your way that you're hesitant about, right? So what do you do? What do you do as a greedy snake, right? Right, we're just gonna call this the greedy snake. Greedy snake. We're just gonna call this the greedy snake, and now we're just faced with this problem. Now this is like money in the bank, and whenever it encounters some kind of negative value, it should hesitate a little bit, right? And it should hesitate, and it should, raise its head and look a little bit forward to see what's next. Because if if we take these two like as a package, right? If we take this as a package, it's still a good package. And actually, we can take this and include any positive value down the line until we hit another negative value as the entire package, and then we can decide if we are going to take this package or not, right? Right. So this is like a package, um, and also we have another package on the right because this is another package that we can consider. It's less valuable because the net value of this package is 0. And the net value of this package is +2, so we better take it. And once we take this package, right? Once we take this package, uh, that's the end of it because there's no more unexplored positive values anymore. There's no more good stuff. It's gonna stop here. So yeah, I think we're gonna just use that greedy snake algorithm to to finish this. Yep. So how do we do that? Uh, how do we implement this greedy snake algorithm? Right. Greedy snake. Rule number one: um, eat as much, eat as many uh, uh, positive values down the line, down both ways. You know, hesitate on uh, uh, on negative values, and then look ahead um, to see what's the package value, what's the package value beyond the the current negative value, right? What's the package value, right? The package value meaning, right? So the package value is the value of the negative, the current negative value plus all the positive values ahead of the current negative value before encountering a second negative value. Right, so we're going to do that. And how do we terminate this process? Terminate when they're when all the packages, lucrative packages have been explored. How do we determine if all the lucrative packages have been explored? Well, Well, I mean, this is still like suboptimal, right? Because even if we just, stop, um, even if we just stop at the, um, because we're only tracking one package ahead, right? Uh, because we're only checking one package ahead, maybe it's not good enough because what if, right, like, what if like there's like a really big negative value somewhere, and beyond that really big negative value, there's a very small positive number, and then again you have a negative value. Then by this greedy snake algorithm, we're basically going to stop at the first big negative value because the package uh, with the big negative value and the next positive value ahead of it is not really lucrative. Um, it's uh, uh, um, the package is not good. It's negative, right? So we just stop there. But that is like short-sighted. What if we have like a really, really big positive value right after the second negative, right? So then you don't want to stop. So I think what we're gonna do then is not gonna do that, right? So this is we're gonna just delete it. That's not a good heuristic. I think then what we're gonna do, uh, I think then what we're gonna do is something even better. Yeah, I think what we're gonna do next is, right, we're at the situation here. We have some money in the bank, and then we're gonna decide if we're gonna jump over a negative value in order to get the positives afterwards. Um, I think in each direction, I am just going to be bold and brave and, stop here, take whatever package there is, right? Take whatever package there is, and even on this side, I'm just gonna take whatever package I can find. Uh, yeah, and then we're gonna store, the maximum. But since we already are colliding with ourselves here, this is no longer a valid. This is no longer a valid snake. Uh, um, right. So what about um, right? How can this greedy snake be globally optimal? Uh, how can this greedy snake be globally optimal? Uh, I think for this greedy snake to be globally optimal, we need mm, 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 to be greed in the right way, right? We probably now need some mathematical proof power to help ourselves think in a more logical way. Um, let's say what happens if we already reached a optimal solution, which is the case of this, right? This is the case where we have reached our optimal solution. Um, in the case of the optimal solution, we can't get any more benefits, right? That means uh, any other package arrangements, for example, this package arrangement, any other package arrangements will will present less value than our optimal package arrangement, right? Right. Um, That means the optimal package deal arrangement um, will be optimal, and then it's going to let's see, it's going to really cost. So what is the characteristic here that we can be looking for? So the optimal package deal since the beginning of this, I think it is. Let's say this will absolutely be optimal if this will absolutely be optimal if um, I'm just thinking what defines global optimal in this case of a greedy snake. Um, well, I'm just gonna pause a little bit and then I'll continue when I got myself some insight. Okay. All right, I am back, and I just think I come up with a new idea. I don't know if it's gonna work, but hopefully it will. All right. So I'm gonna explain my new idea here. So what is the new idea? Um, I'm not going to talk about the greedy snake anymore. I'm going to talk about reward reward packages, and you know we're gonna have reward packages uh, 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 and costs to get them. And what do I mean by that? Well, let's just say we're still working on this case too. To include, uh, the -2 thing here in the in our optimal array, right? So we're still left with this problem. And what we're gonna do is that we're gonna basically flag every negative value down our road as costs, right? Because those are costs. And we're gonna identify packages. Um, so these are our negative values, and we're gonna identify packages. In this case, this +9 here, it's a package, right? Packages that we can get after we pay those costs. Um, and then for each package, this is my idea here. Like for each package that requires a cost, um, we evaluate the cost to get the package reward from both sides, right? Meaning to get this package from here, we need to pay a cost of -7. You know, from here we need to pay a cost of -9 in order to get to this package. -7 in order to get to this package. So, excuse me, excuse me. Gonna get some water. So once we're aware of these costs, now we can compare the costs and decide. Now we're at the forefront of it, and are we going to use these numbers -7 or are we going to use this -9 in order to get to 9? And obviously we're going to use -7. This is a pretty trivial question, right? So yeah, we're going to take it from here. So this is like a no-brainer. But when problems get more complicated, let me just introduce a more complicated problem, and then we can demonstrate how this might work in more complicated cases. Let's say, all right, let's say we expand this list a little bit. We still start from -2, but we're just going to add much more negative values in between those. Let's add a -3 there. Maybe another -5 there, or -6 there, right? Yeah. Uh, so we're gonna have a lot more negative values on our way. Yeah, let's maybe add a few more. We're gonna have another small package of 2 here, right? And we're gonna meet a -4 here, right? So we're gonna build our problem like this. It's more general, it's more complicated. Like before, we're gonna draw a ring here. That's a good ring. And then of course we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. 12, just like the clock. We have 12 marks. So this is 12. That's number 11. So we're going to just write them down one by one. At our 12 o'clock, we're going to have our 0, 0, and then 1 o'clock, it's going to be -3. 2 o'clock, it's 5. 3 o'clock, it's -6. 8, -9. A 9 here. Let's write this a little bit down. Yeah, -9, 9, -7, 2, -4, 3, -2. Yep. So this is our array, our list. And then let's change the color and start exploring. Orange. So we're gonna have to start from -2 because that is our anchor point anyways. K is there. Uh, yeah, this is our K. We have to include, so our snake, it will definitely have to include this value here, right? This is the root of our snake, um, heart of our snake, right? Let's say heart because the snake has to have a heart. It's the heart of our snake, and then we're gonna now start labeling or grouping, packages. Now, this is not really a package because we can just grab it. This is a package. This is a package because it requires some costs to get it. This is a package. This is a package. So I have 4 packages, and then we have, a few gates. This is a gate, right? We're gonna just, mark the gates using like not here, gates, right? Yeah, yeah. I think gates is a bit much better word to use here, through which to get them, and gates through which to get them. Yeah. So we have package rewards, right, or treasures, right? Uh, Reward packages. You know, let's call them. Just to make it more fun. Let's call them treasure chests. Uh, for each chest, that requires a gate. We value the cost to get the chest reward from both sides. I mean, at this point, it doesn't really matter how much is worth in that chest. As long as it's something, we're going to have a preference of whether of which gate to use. For example, we have another gate here. Yeah, for example, For this first treasure chest here, um, would you rather um pay let's say pay $4 to open this gate, or would you rather pay $7 to open this gate? Of course, you're gonna prefer to prefer to use this gate for that reward, right? I don't care how much reward is right there. And for this 9 here, you compare -7 and -9. Of course, you're gonna prefer to open this gate to get that. Uh, Again, I don't care how much reward is there for now. And for this reward, for this treasure chest here, would you rather use 6 or would you rather use $9? I would rather use $6 to get there. And for this chest here, would you rather use $3 or would you rather use $6 to get there? Yeah, I would rather use $3 to get there. So we've already kind of like drawn our treasure map, like almost like an indicator of where we should go as the most economical way to crack our treasure cases. And it just so happens that that they're all going in the same direction. I'm surprised. But maybe let's just in order to make this more interesting, we actually want to change some values in here. Let's just change that -3 to what? To -7, just to make it more fun. Because now we're gonna have to change this direction now, and let's see what that, whoops, what that brings us. All right. Now this is -7, right? And because of that, we're gonna have to prefer this one to open the door to get to that chest. Yeah. So here is a more interesting case now, and it is not obvious yet, like how we should uh, process the things here. Um, I mean, on the counterclockwise side of things, things are more obvious. For example, uh, the indicators all indicate that we should just go counterclockwise and crack these doors open, pay the $4 and $7 to get the $2 and the $9, right? Because why not, right? Because you pay $11, well, you unlocked a $2 and $9. Yes, I mean you earned nothing, but then you are exposed to more opportunities down the line, right? So that's definitely a yes. So this is already like money in the bank for sure. Uh, yeah, although it's like the same amount of money uh, as if we stop at this number 3 here, but we actually traveled more further down here and we're exposed to more opportunities. So same value gained, exposed to more downstream opportunities. Why not, right? So this is definitely money in the bank. What about this side? Are we going to travel any of those paths down there? You see, mm, what these arrows are suggesting us is that, um, it's not really suggested to go busting this door. But again, it is also not suggesting that we bust this door either. So this is more like a black box. There's no suggested route to go anymore. No preferable door to crack. None of these doors are preferred. Uh, 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 uh. But what if we want to make things more interesting? Because now actually these ones are not lucrative anymore. You have to pay 7 to get a 5. Come on. Uh, and then you need to pay 6. Well, if you pay 6 to get an A, that's good. Um, um, but then that cancels out when you need to pay 7 to get a 5, right? You have a net loss of 2 and then you get a net gain of 2. Um, but if you can combine, the entire four of them here, it's still, a good thing to do because although you have zero gain overall, but you've traveled down further in the loop. But let's just make the game a little bit more interesting. Uh, uh, let's make it not worth going. All right. Um, let's. Yeah, seems like right now what we have is like uh our total value is like -2, 1, so that's -2, 3. So that's total value is 1 at this point. Total value is 1. Uh, and it looks like we're never gonna get any better. The only way to make this, more worth it is to actually raise these values inside. And that's what I'm gonna do. I'm gonna actually change this value to something like a 10, make it lucrative, okay? So that means I'm gonna change in this now to 10. Now there's much more incentive to go down there, but still we didn't know about it, right? Because we just said when we were drawing these arrows, we didn't care about how much value was in those treasure chests. Uh, but now, knowing that this is a pretty big reward, it is more tempting to actually go down the road and to try to get it, right? Um, but these arrows don't tell you that. These arrows only indicate, a preferred door to open with respect to the reward there. But it doesn't tell you whether you should actually take it. It just says, this door is better than this door. That's what it says. Um, but whether it's worth opening or not, it only tells you, this is a preferred door than the opposite door. That's all what it says. Uh, so then it looks like if we don't know the reward values in there at all, then we're basically at a stalemate. We're at a stalemate here. Um, at a stalemate. Sorry, I'm gonna use this color. We're at a stalemate because we don't know. We don't have any information uh, behind the doors to tell us whether we should really move on or not. Like, right? These things are black box to us. And actually, when we actually busted these two doors, the -4 and the -7, we weren't really evaluating their value at all. These chests could be completely, worthless, like having values of ones and twos. Uh, so it would cost more to actually bust the door open than what we get in the treasure chests. So we definitely still need additional uh, uh, information to help us. We do have those information, but those information come at a cost. If you want to, have some recon information on what is the reward in those packages, right? You're either gonna have to use memory to memorize them, uh, uh, or you are going to yeah, somehow find a way to know what they are. So uh, let's say, right, let's say what is the value of opening any door at all, like, right? What is the value of opening this door? Door value, right? Because the door value, the door value is determined by the treasure, the hides behind the door, right? Um, um, Now if you, but depending on which direction you open the door, you're gonna have a door value. Okay, let's actually have two sets of door values, right? We have a clockwise door value and a counterclockwise door value. Um, let's mark it right clockwise as 1, counterclockwise as 2. All right, just these are our notations. So for this door right there, where's our marker? Yeah, for this door right there, uh, value of value of 1, which is like to open it in clockwise fashion, is -6 plus 10 is 4. The door value of this in the counterclockwise fashion and the counterclockwise direction is -6 plus 5, so this is -1. So right, and then this door, its V2 is what? I mean, this is already like this is what we already got, like money in the bank, right? So we have no extra gains if we bust this door open in a counterclockwise way, so it's -7 to do that. Um, so the door value of opening it in the clockwise direction is what? Like the immediate door value is 5 minus 7 minus 2, right? So if we just write these values on the door here, we're probably still not gonna bust them open at all. Let's write this door value here. So door value of opening it in the clockwise direction, V1, value 1. This is gonna be 0. No, actually not 0, -9, because we already have what we have. Yes or no? No, 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 no. That's not the case, because if we're talking about door values, we're no longer considering these sections as, money in the bank anymore. Whoops. Let's say, yeah, we're gonna just no longer assume that we are getting there. So these are the money in the bank. That's all. Um, so we're gonna just reassess the door values door by door. And if we do it in a clockwise way, the door value is 0. In the counterclockwise way, the door value is actually 1. V2 is 1. Uh, what about this? Um, if we go clockwise, our door value is going to be 2 minus 7 minus 5. If we do it in a counterclockwise way, it's actually 2. And for this, our V1, V2 is 0, or actually -4, because these are things that we already have. And the value for going in the, sorry, this is actually V1 is -4. V2 is -2. Right, so these are like the immediate door values here. And looking at these things, they're just horrifying. Like, right, they're just terrifying, right? It's, oh, -4, -7, -2, -2. While we're doing them, right? We just stay where we are. But then you're gonna miss the chance to get this really big value here. So those are the immediate door values. They're not really helpful. They're basically gonna stop you from moving at all. Uh, that's not enough incentive. So we need more incentive to encourage us to travel down, right? Like, because some of the values we can accumulate. For example, if we travel clockwise, counterclockwise with this V2, it is going to be it can be stacked, right? It can be stacked with this V2 here. Uh, 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 um, and of course, if you want to get those v2 stacked value, you're gonna have to pay this value as well, right? So you can combine any of these v2s here uh, uh, um, in any way you like, right? So we're gonna have like a v2 array, uh, uh, um, and then we can perform the door value array um, as we go, and then decide we want if we want to travel down, right? So let's just write our so for our doors, right? Like we have one, two, let's say one, two, three, four, five. We have five doors, right? We have five doors. And we're gonna list them as 0, 1, 2, 3, 5. And we will have a V1 array. We'll have a V2 array. For the V1 array, uh, the first one is -2. The second one is 4. The third one is 0. The fourth one is 5. The sixth one, the last one is -4. And then for the V2, which is going counterclockwise, the first one is -7. The second one is -1, right? And the next one is what? 1. Yeah, and the next one is what? 2. Yeah, and the next one is what? -2. Right. So how are we going to choose them? How are we going to choose them? Well, let's go back to the orange color. Like if we decide to go, to crack the doors in the clockwise direction, we're going to look at this V1s, right? The door of V1s. And we can take a streak of them, right? We can take a streak of them and stop at any point. Like we can stop here and we can basically loot this 4 and this 5 value. We're gonna lose something at the first door, but that's about it. And then we're gonna gain more, right? So the total gain, right? The gain, let's say the gain, the max gain, right? The max gain of going each way. This is clockwise, right? V1 is clockwise. Clockwise. This is counterclockwise. Um, so the maximum gain of going clockwise to crack those doors is if we take the first 4 doors and we leave the last door closed because yeah, behind the last door is already something we've explored. The max gain, so it's actually cracking all the doors we can, and the gain here is how much? 7, right? Uh, and then if we go in a counterclockwise direction, we're losing, right? We made equal, we're gaining something, and that's pretty much where we stop because down the line those are losses. So if we are traveling counterclockwise fashion, our total gain is just what? 1. So the option is kind of like obvious, um, where we want to go. But do we want to go both ways? I mean, if those two actually don't overlap and they're both like ludicrative in a way, we of course can go both ways. Um, but in this case, I mean, this case going uh, going clockwise definitely a win, right? Yeah, yes, yes, yes. So this is definitely what we do. So what is the total gain? Um, we gained 7. So initially we have what? Like the reward is like um, reward is 1, like initially, that's the money in the bank. And then we have, if we go clockwise, we're going to add 7 to our bank. So the total reward is going to be 8. Uh, and I think this is the optimal calculation. I'm not too sure, but I think it is. Can we prove that this is like the this is like the optimal way to go, right? We use doors, right? And gates or doors, for which to get through them. And then, so this, right, we calculate the the value, the door value, the gate value, or let's say door value of, you know, opening each door on in clockwise or counterclockwise direction. Then we decide how many doors, which doors, yeah, which doors, which doors to open on counterclockwise or counterclockwise direction. Right, in in that direction. Right, in the counterclockwise or clockwise direction. Yeah. So this is our intuition, basically. And I think it's a working and a globally optimal intuition. I'm not too sure, but this is just you know, my feeling. My feeling is that this is globally optimal. But can we prove it? Can we prove it? Um, uh, can we prove it? Well, I mean, if we can find, an even better solution than what we already have, right? Then that definitely means that for one of the doors, for one of the doors we have, for one of the doors we have, for one of the doors we have used a different. We either didn't open it or we opened it in a different direction. So if we opened it in a different, so what for any of these doors, if we opened it in a different way or we didn't open it, then we can still like express it in this v1 v2 lists, right? And if there exists like a better solution, it will be expressed in using a different line. Let's use what? Let's use yellow to represent that counterexample. For example, let's say let's say just randomly, okay, um, a different decision on our door choice is going to be better. For example, we say that this is the better choice, okay? We said this is a better choice than this one here. Then we're gonna just verify if that's true, right? Um, and then we see that this is exactly what we calculated before, and it was inferior to what we had. Or if we say that this is the best reward, but then we're gonna compare it with what we had before, and we see that this is actually also worse than this because you are opening like a worthless negative value door in addition to what we did, what we tried our best in the counterclockwise direction. So again, this is like proved to be wrong. Yeah, if we are using like the positive direction and we we argue that this is like actually more optimal way of opening it, then we can just prove by contradiction, saying that hey, we compared that with our current best, and we see that what you have proposed as a better solution actually missed a few more points down the road, so it's definitely not as good. So I think we kind of like, at least in our mind, intuitively proved that this is the best intuition, the best, the globally best of what we can do. So this is what we're gonna do to implement for our second case, right? For second case, when we have to include this -2 here, like the heart of our snake, yeah, we're just gonna call this what, snake heart, right? Just make it more fun factor. This is the snake heart. Um, yeah, this is a snake heart. Include the snake heart. This is like the snake heart. Include the snake heart in the array because the snake has to have a heart. All right, and in this case, we are gonna use this a door value approach. Let's call it like the door value approach, right? And door value approach. This is like, come on, door value approach. Yeah, this is like the door value approach. We use this door value approach to solve this problem. And okay, and we start from the heart, the snake heart, right? And then we're gonna evaluate what's like our money in the bank, right? Yeah, yeah. So let's write this down. Let's write this down as this is uh okay. Let's say money in the bank, money in the back. No, money in the bank. So this part is the money in the bank that we already have. And then we're going to evaluate the remaining values of those doors. Right, right. So how are we going to do that? Well, we're just going to directly implement that code, okay? So for the first stop, let's say max sub case 2, first stop this, first stop that. Yeah, so we're definitely gonna hide these two things here because I think these are unsuccessful attempts. We're going to define our new function called def max sub case 2 of door value, right? Version 2 solve k nums, right? So this is our version 2 solution, and solve the circular max subarray with a given knowledge the case in the max subarray. Yep, the descriptions are all right. Uh, uh, using a door value intuition. Door value intuition. So each of the remaining negative indices are, doors, and the positive values trapped between doors are, you know, treasure chests. We want to list the door busting value of each door from either clockwise, excuse me, direction or counterclockwise direction. Then we form a door, we form two door value lists, one counterclockwise, one counterclockwise. Then we use these two lists VCW and V counter CCW to decide which doors to to bust, to open from which side, in order to get the optimal um, uh, uh, optimal reward for the snake, right? Index K is the snake heart, which the snake has to cover, right? So that is that, and that is our approach, and we're just gonna follow this, and let's just first calculate what's money in the bank, right? The first step, find money in the bank. Near snake heart, i.e. all the positive values next to the snake heart. Right, so MIB, right, money in the bank, MITB, I'm just gonna call that. Let's initialize it as numsK, right, because that's the value of that. And we're gonna do while loop, while k, if we travel, yeah, we travel, first travel clockwise. So if we're traveling clockwise from k, that means we're increasing our indices. Right, so while k, um, um, shall we rearrange the nums list so that, it'll make it easier uh, for us to work with? Don't you want like the snake heart to be uh, right here, right? It's probably a good idea to do that. I'm just gonna reset I'm gonna just shift the nums array so that the snake heart sits at the um, mm, mm, at the last element, or the first element, or the last element. I don't care. I mean, it's probably better to sit that at the first element, right? The snake heart, or the last. I mean, it doesn't matter. But since we have drawn this uh, as the last element, we were just gonna no. Actually, let's do it in this way. We're gonna shift it to the first. So it's not that hard, right? We're just gonna shift this to the first, so it'll become like this. Yeah, What we just need to do is to just remove this and then put a black line right here. This is where we start, and snake heart. We want our snake heart to always start at 0, right? So now k equal to 0. This is going to be easier later on when we do that. Yeah, we're going to just add a small line here. We shift our nums array so that the snake heart is always the first element in nums, which is fine, right? Yeah. And we're just going to deal with the shifted nums array. Shift the nums array, nums list, so that the snake heart is always at index 0. This facilitates code readability later. So we have had some experience, shifting codes, reconstructing codes, right? So we're gonna do nums nums shifted. You just call it shifted, right? Shifted, right? Equals nums. Let's say we start from k, right? Start from that index all the way to the end with a increment of 1 and plus um, um, nums from the beginning all the way to k, uh, uh, k plus 1. No, not k plus 1 because we already included k in the first one, uh, uh, through 1, like that. Right, so we shifted it, and then um, how about let's say nums2, right? I think that's easier to work with. So nums2 k. This is like the money in the bank. We already have the snake heart. We cannot remove the heart. So while k, let's travel clockwise. Um, while k is less than the last element, while k is less than the length of, right? We better just use that. N equals to nums, no, length of nums2. Well, that is less than that, right? Um, less than n, yeah. We're going to see um, if nums2 of k is less than 0. If it is less than 0, we're going to break. Else, we're going to add the money in the bank with whatever this is, right? Nums of k. And we're going to initialize k with what? K is 1, right? So initialize that, and we just initialize with k equal to 1. Wait, what if it only has one value there, right? What if the nums array only has one value in it? If that's the case, then if n is equal to 1, we simply just return nums 0, right? Yeah, we should probably do this even earlier in the game. Lens nums, if that is like that, we just return that. Um, then all the cases down below, we have at least 2 elements. And while k is less than n, we're gonna see if it's a negative value. Otherwise, we're gonna increase that. We're gonna do it again for the inverse direction, right? So now, if we travel counterclockwise, we're gonna look at we're gonna start, of course, from index is gonna be -1, while yeah, so we're gonna start initialize k equal to -1, or shall we say the last one? Yeah, and while k is greater than 0, if nums2 of k is less than 0, if we found something like a door there, we're gonna stop. Otherwise, we're gonna just continue to take the money in the bank. Nums2 of k. Yep, this is like travel counterclockwise, travel clockwise. Right, we find the money in the bank. Right, that's the first step. And what about the second step? Step 2. So after we have found the money in the bank, we're going to now see how many doors we have, right? And for each of these doors, we're going to assign a 2 values, right? Yeah. Yes. But how do we determine like this is like the first door? Well, you know what? Actually, we would never bust the last door hard stop. Like we would never bust this door. Like that's a no-no. The last door, we never bust it because if it's like already like at the end of it, there's no reward, right? So we never bust these 2 doors. So that is like a no-no. It never, yeah. So because it only has costs and it has no gains. So we're gonna assign the cost of these 2 doors with uh, uh, yeah, whatever value they have uh, on this side. I mean, it doesn't matter. We're never gonna bust them. Just like this one here, doesn't matter. We're never gonna bust it. So we're only worried about So we can still calculate whatever value it is there. Um, but we're just never gonna use it, right? We can use this number as none. It's fine, none, because we don't need to calculate anything. We can just assign these 2 numbers as none because because we're not going to use them. So yeah, we better just assign them nones for simplicity. Yeah, save some computation there. So how are we gonna travel our way? Yeah, we're gonna uh, uh, label all the doors, label all the doors with, not label, list the doors, list all the doors using a for loop with their uh, um, respective clockwise and counterclockwise values, right? So we're gonna use a for loop to somehow find out about that. I think, yeah, K, right, K1. Let's just say this is like K clockwise because I think these two numbers still have value um, to be separate. K counterclockwise, right? Right. So now we have this K clockwise and K counterclockwise. They're gonna end at those breaks. And we're gonna define those numbers as our money of the bank. Oh, we need to, you know, K plus plus, right? K plus equal to 1. And this here is K minus equal to 1 as well. So, so yeah, we're gonna have a clockwise K. Uh, we're gonna have a counterclockwise K. So we're gonna just put it there. Yeah. Um, this is gonna be our this is gonna be where our K clockwise is, and this is gonna be where our K counterclockwise is. Yeah, and now we're gonna, in between. We know that it's gonna be in between K clockwise and K counterclockwise. Yep, it's gonna be like that because uh uh right. We better check because there's some maybe special cases. If K clockwise is somehow greater or equal to K counterclockwise, right? That means we're overlapping. And when we're overlapping, this means all the values are money in the bank, right? If these two indices overlap, it means all values are money in the bank. So what we do is that return uh, uh, um, we're going to return the value as what? The max sub case too. a sum of the nums 2, right? Yeah, sum of nums or nums 2. Doesn't matter. It's the same thing. So if it's not the case, we're going to move on here and we're going to use a for loop to start from this index to that index for k in range kcw all the way up to kccw uh, in the step of 1, right? Um, we're going to check if any of the nums2 of k is less than 0. And if it is, that means we found ourselves a, let's say we found ourselves a, mm, we found ourselves a door, and we're gonna start building the arrays, right? Like what arrays? VCW equal to something, and then no VCCW equal to something. Can we build that? And then we're gonna do, of course, our and we're gonna move on, and otherwise or something, right? Um, Otherwise, we're gonna continue growing because if it's like it's uh, a door at k, otherwise it's either door or a treasure chest at k. Right. We better keep like an index, right? So n doors. We're gonna initialize it as 0. Initialize number of doors found, right? And we're gonna search for our doors here. If the value is negative, we found a door at k. Uh, then we're going to give the value of going clockwise as what? Uh, as mm, the as the forward value, as the value downward, which we don't know yet, right? The value downward, let's say we don't know, or value downward, forward, value forward, until next door, uh, minus the cost of the store, right? Minus the cost of the store. That's going to be the value. What about the counterclockwise value? Um, the counterclockwise value would be, the value of those chests that we have already accumulated along our way, right? So current reward is 0, right? Because if we start from current reward accumulated going forward, going clockwise, initialize, right? Initialize. Because we're starting from an index uh, within the money in the bank, so the accumulated current reward accumulated is going to be reset to 0. Um, so the counterclockwise reward is going to be current reward minus the door value, right? And then, yeah, we're probably going to append, right? Python list append to the end. How do we do that? Append is just animals dragon, animals append meerkat. Yeah, we just say append. It's fine. So vcw.append, uh, right, it's gonna append like this. And then for this one here, we just append this value. But we still have to define what is the value forward until next door because we haven't traveled that far yet. We don't know. Okay, we haven't traveled that far yet. We don't know. Uh, right. And if we are just meeting a treasure case, we're going to accumulate the current reward, right? With that treasure case value. Um, yeah. And then at the end of it, we're gonna just increase k by 1. So that's the end of the for loop, but I think there's something missing here because the value forward until next door, this is something really missing here. Because the value of going clockwise is something we don't know, right? Okay. But there's something we know. Uh, are we going to store those things there? I don't know. Like maybe what we do is right now we just don't update that because there's no way of doing it. Uh, and then we're gonna just use another for loop to travel from counterclockwise all the way to clockwise, right? Using a step of -1 to do the same thing here. If, right, the value is like that, uh, mm, well, we're gonna just current reward. We're gonna reset that again to 0. And then a door at K, right? So then VCW going clockwise. If we are going to bust the door open clockwise, it is the current reward, right? Yeah, dot append uh, uh, current reward minus nums 2k. But but this is like a list that we're accumulating in a reverse order. We probably have to end up flipping either VCW or VCCW in the end. But that's fine. We'll deal with that later. Else is when it's a treasure chest at K. Then we're just gonna accumulate that current reward. Call it nums. Okay, and that's it. And K minus equal to 1. Right. And then we're gonna have to flip one of them, right? Flip. Let's say we want to keep everything in the clockwise order, so we're gonna flip VCW, right? So VCW equals to VCW. Um, the last one, to the first one like that. Yeah, this is gonna flip it. All right. So with the respective CW and CCW values, VCW, VCCW, right? Yeah. Now we have those two. And what do we do? Now we have these two lists, right? VCW, VCCW. Now let's see if we travel down in the clockwise value list, what's the maximum we can get off of it? And let's try if we travel down the negative value list, and what is the value we can get off of it? Let's see. We got 5 doors in this case, and the first door. So how do we find the optimal value going forward? Uh, uh, um, Going in the clockwise direction. I think when we start here, it's not looking good. It gets because it's negative, but we still move on anyway because right there could be a good stuff down the road. So you just never know. You just try everything, right? You just try everything uh, until the second to last, and then keep a maximum there. Right, got it. So it's gonna have to be a for loop. Uh, um, hey, can we actually calculate it during this for loop here? Because we're doing that anyways. Right, we can do instead of VCW, we can do V1 accumulative and V2 accumulative, right? Yeah, yeah, yeah. Exactly. This is an improvement, right? We could do we could do VCCW accum. Oops. Um, we can do VCW accum, VCW CCW accum instead here. Yeah, because if we do that, uh, we don't need the calculation here, right? We just read which is the largest of the accum, and we just take it. Yeah, and with the respective cumulative, even better. We um, we calculate the accumulative uh, uh, VCW accum uh, VCCW accum um, in the same loop, the same for loop, and save ourselves for the next computations. So in that case, if we found like a door, we're going to append our VCW, right? Let's just say VCCW is an empty list, uh, and VCCW is also like an empty list. Uh, now Since we found our first door, our CCW cumulative is going to be V CCW like the current last element in it plus the VCCW uh, last element in it, right? The latest element in both arrays, right? Um, right. So same thing here. VCCW cumulative, it is going to be VCCW VCW cumulative, uh, and then the last element plus VCW last element. Right, we're going to add the cumulative values here so that that saves our computation. Um, right, so we're going to initialize those here as well. CW cum VCCW cum. Maybe eventually we can remove these two arrays, but not yet, not now. We are going to basically leave them here for now. Uh, and yeah, and then see if we can remove them later. So VCW, okay, flip VCW, VCW accum as well. So we're gonna flip both of them. Right. So now we're gonna have cumulative arrays now. So what would they look like? I mean, this is like super interesting to find out. I am going to actually push these things upward. Yeah, I mean, let's just kill some of the useless things in here. Uh, and then 5 doors. Yeah, we know there are 5 doors. We move this up. Move this up a little bit more. All right. Yeah, it's pretty much as we can go. CW. Right, and then yeah, we could do those. That's exactly what we're doing. Uh, we will do VCW accum and VCCW accum, probably with an enter in between. Right. And how do we do it? Well, let's see. Now, what we're gonna do is that we're gonna, whoops, I clicked on the wrong thing. Let's see if we can do that. VCW cumulative. Now, so at the beginning here, it's gonna be -2, right? It's the same as the V1 list here. But once we move on to the index 1 here, we're gonna just add up the two values here. So it's gonna be -2 plus 4, it's gonna be 2. And then here we add a 0 to it, it's still 2. Here we add a 5 to it, it's gonna be 7. and we do a hard stop. We don't really do anything here, but yeah, we don't really need to do anything there because we're not going to look that up at all. Whatever, this is going to be whatever it is because we're not using it. Uh, and then for the other direction, so we do want to accumulate that, in the reverse order, and then we flip it back. Yeah, so right now it's at -2, right? And then this is what at 2, no, 0, right? And plus 1, it's going to be 1. And then with the -1, it's going to actually be -1. And we don't take this one at all, right? We don't take that at all because it's the last door and we don't really need to bust it open. It just opens the door to our money in the bank. We don't need to do that. So we're just going to look for the maximum, you know, in all of these, right? And that is going to be our solution. And it's clearly this one, 7 here, because, it's larger than the 1 here. So we are just going to look at the maximum. In both VCW accum and VCCW accum. Right. Right. I think we may not even have to flip them because what's the point of flipping them, right? Um, anyways, maximum. Are we gonna return like the maximum reward? Yeah, we don't need to tell uh the output like how do we achieve it. We can just say that, that's how we achieved it, right? Take the larger maximum, right, in both of them. So we just take it, right? So we're gonna do a max operation. This is gonna cost some VCW accum, and then another one is at this point we can just concatenate them. Doesn't matter. VCCW accum because we're just gonna find the maximum value in them, right? Right. And these two values, they're not gonna matter at all. But uh, uh, um, but have we assigned any value to them? We did. So let's not write an A because it's gonna confuse ourselves when we look at this again. So we're just gonna use whatever they are, okay? Because we calculated them. This is what we're doing clockwise, right? So this is gonna be 7 minus 4, what, 3? So we were doing this, -2, 0, 1, -1 plus that is gonna be -8, right? We're gonna find the largest in these two arrays. So we're just, you know, concatenating them, and then we just find the maximum there. Uh, and what do we do about that? Well, those are like the maximum value we can achieve by busting doors. And we're going to add that up with the money in the bank. And that is going to be money in the bank plus this. Yeah, this is going to be the return value, right? So overall, we either return the first element if our list only has one element, or we go through these finding money in the bank, uh, uh, you know, calculating door values and the cumulative door values, and then summing them up and then returning them. going all the 9 yards there to get to the answer. I'm sure, there's probably some flaws and, misconsiderations in here, but let's just give it a try, okay? Right, there's something wrong. Okay, right, there's a function name issue here. In the main function here, we were saying we want to use max case that, but we're now going to have to use the version 2. Something's wrong. List objects no attribute append. Huh. Okay, I think we're missing one P there. Append has double P's. So rare. There you go. Does it give us a value? Not really. It says list index out of range. Okay. VCCW accum append. So what is the log here? You're telling me that the index is out of range. -1. Excuse me. What does -1 do? For example, if you have a test list of like 0, 1, 2, 3, right? On test of -1, what does that give us? 3. So it is fine, right? Accum. But what about the accum list? Oh, okay. So at the beginning, it's an empty list. That's what you're saying. I got it. I mean, so at the beginning, it has 0 elements, so you cannot even look it up, right? This is tricky because you need an initial value of them. Right, right. So somehow you have to initialize it with at least one value in it. Or let's you know let's make it easier for us and use if empty, right? If length of this accum is 0, then we simply append in this manner 0 plus that, right? Else, then we append in this way. This is gonna take care of the first case where when we don't have any value in this here, right? And we're gonna do the same for this guy here. If length of VCW accum is equal to 0, right? We're gonna do the same append, but just replace that with the 0 here. Else, we're going to append with its original, with its last value, right? Let's hope that this fixes it. Maybe we'll just come into another, okay. So this is getting us 28, which is unexpected because, yeah, the index we found is like K, is 7, it's fine. We're just looking at this. The first case result is 13, which was correct, but the second case result is 28, which is definitely not correct. So how do we get to 28? Because, you know what? We're returning money in the bank and we're returning the cumulative, the maximum between that and that. So we do want to, start our debugger, and then we want to put a debugger there, put our breakpoint there. Well, it didn't really break anything. So we're going to restart the kernel and clear all outputs. And we're going to start our debugger. And then we are going to put our breakpoint right there at the end of the new function to see what is exactly each of the components that we come up with. So we have this money in the bank. MITB is 19. Does that make sense? I think it doesn't make sense because the real money in the bank is what? We have a 3 and we have a 13 right there. So the money in the bank, it should be 14. The money in the bank is 14. Yeah, the money in the bank should be 14 instead of 19. There's a difference of 5 there. So I don't know how you came up with the money in the bank of 14. We definitely need to find out how you came up with that money in the bank because it was wrong. So let's put a breakpoint here to see what's the money in the bank that we calculated traveling clockwise, right? And let's just stop this here. Well, we have to restart the kernel each time, I guess. So there's some mistake in the money in the bank calculation. There's probably some mistake uh, in the door value calculation as well. So we'll get them all. Don't worry. It'll take some time, but eventually we'll get them all. Now the debugger is started. We're gonna put our breakpoint here, and then run that and run this. And we'll be looking at, the money in the bank after traveling clockwise. So we should be expecting money in the bank to be, let's say, where did we start? Money in the bank. So we're starting at the second element, right? Well, we're like starting. We are initializing it with that, with this value here, right? So it does include the -2 already. So okay, so we're expecting the money in the bank calculated to be -2 plus 0 plus 5 plus 8. So it'll be 13 minus 2, so it should be 11. But now our money in the bank is actually what? 16. And where does our k end at? We expect our k to end at, to end at the first negative value. The first negative value, and did it end at the first negative value? So 1, 0, 1, 2, 3, 4, 5, 6, 7. Whoa, it didn't. like you see, K actually went all the way to 7. Wow. But isn't it like, didn't we break? I mean, I basically said that nums2, oh, because nums2 is a different nums. So nums2 is a list where we started from -2, and then 0, 5, 8, -9, 9, -7, 3. Yeah, but still, in that case, you should stop at 4 instead of stopping at 7. Oh, it did stop at 7, 4. Okay, okay, fine. KCW is at 4 right now. Okay, which is correct. And we haven't initialized our K yet, so let's just step forward to see what happens. I mean, if our KCW did stop at 4, then how come that currently our MITB is already 16? Because if we add up all the values in there, it's going to be -2, 0, 5, 8. So it'll be 13, and -2, it'll be 11, right? So I don't really understand that. K. Oh, okay, okay, wait. Why is K 7? Right, that is the problem. We have relisted we have shifted the nums list. So now after we shifted it, right, we're gonna reset K. Reset K to 0, because now the snake eye, no, the snake heart is at index 0, right? So that's what we do. And now let's see if we get the right answer. Who knows? Right, 13, 23. It's still not correct. Still not correct. So it's still going to be some problem in here, and we're going to see. Yeah, we're going to still set a breakpoint here and see what happens. Clear all outputs. Be patient, guys, because we're almost there, and I believe we're very close to a correct solution. It's just that we have to go through this debugging process to work out any of the logical fallacies we had made in our calculation. So I'm going to put a few breakpoints here. A first breakpoint here to see what is MITB in the positive direction, and then another breakpoint here to see what is the accumulated MITB after going in the backward direction as well, and then current reward, we reset current reward, right? And then we're gonna just basically see these 4 arrays, VCCW and things like that, right? So that being said, let's go there. So the first breakpoint is where we start, is where we have finished first half of the money in the bank calculation, and it's 11. That's correct, because the money in the bank, if we're going forward, is going to be -2 plus 13. It's -11, and our KCW should be 4. And that is correct. And let's move on. to the next breakpoint, and our money in the bank. Um, why is it like still 11? Because hold on, because we think, now we're going backwards, right? Going backwards meaning we're going to start from number 3 here. So that's definitely a plus. So why isn't that 3 added to money in the bank? So that's some problem right there. And we're going to stop it there. And we're going to rerun it. Oh, after rerun, I guess those breakpoints no longer worked. So I'll just have to restart the kernel. This is something inherently, I guess, ill-designed in the Jupyter lab, that each time I have to restart the kernel in order for the debugger to work again. Now let's set our breakpoint at the place where we have updated our first half of the money in the bank, and then we're traveling into the second half of the money in the bank, right? So we basically just set our breakpoint there and cancel that breakpoint. All right, and let's get started. Right, so right now money in the bank is at 11, and then we're now uh, trying to calculate backwards for our money in the bank. Let's take a look at nums2 right now, the shifted list. So it's -2 and then 0, 5, 8, -9, 9, -7, 3. It is correct. So we have done our job, going forward and calculate that. So when we calculate backwards, work backwards to calculate money in the bank in the other direction, we really want to, let's say, we really want to start at index 7, right? So KCCW starts at 7, that is correct. And nums2 uh, of KCCW is nums2 of 7, which is number 3. So it definitely is not less than 0. So we take a step forward, and it's going to actually add to that value here right now. So MITB 11, KCCW is 7. I think after this step, it should jump to 14. Right, yeah, MITB is 14. And then we are reducing KCCW by 1, which makes sense. Let's do that. So then we are at the value -7. So our KCCW is 6, and at index 6, the value is -7, right? And because now if we step again, we found out that indeed this number is less than 0, so we just break. Right, we just break. And our MITB should be just 14, right? Yeah, we just break. We break the for loop, and that should be it. And my MITB is 14. Um, and our CCW is still larger than CW, so we don't have overlap. Um, so it should be fine. I mean, money in the bank is 14. It is correct, right? Yeah, so money in the bank is still correct. I don't see why it's incorrect in the previous case. It is correct. The money in the bank, it is correct. Um, so we can now, I guess, try to put another breakpoint in front of uh, um, this 106, and then put another breakpoint in front of this, just to see what we've got after those things. Where are we? Where are we here? I have no idea why we're here. Okay, here we go. So for the VCCW of accumulated list, uh, it is a 9, and VCCW list, it has a 9 as well. So um, let's see. So these are the boundaries of our money in the bank. So, and we have two doors. One is a 9, one is -9, one is -7. I just don't know how we only have uh, a length of 1 for VCCW list, because I would expect, if we travel down from index of uh, uh, 4, like 4 in nums2, right? In nums2 from 4, that is like -9 down to -7. If we cover those indices, -4 and all, 4 to 6, we definitely will cover two doors, right? So how come? I mean, when Kate is at 4, we will have appended a VCCW value to it, right? And uh, what is the value that we append? Current reward, which is 0 to begin with, and then minus. Oh crap! It should be a plus. First of all, it should be a plus because the door value is negative. So we don't need to use another negative here. We just use positive. That's one thing to pay attention to. And the next thing is, why is there only one value in the VCCW list? There should be two, right? Right, there should be two. So after you've done that, and you will basically, append the accumulated VCCW list as well. Um, and you're gonna move on to the next one, number 5 list, which is like gives you a 9. Yeah, and then because this is a treasure chest, you don't do any of those. You just add the current reward. Uh, right, with that. Right. But don't we? I mean, when we are busting doors, right? Don't we append the current reward, like update the current reward as well? We need to, right? Yeah, we definitely need to. So those are the two things I found immediately wrong here. One is that even if we are at a door, we still need to update our current reward with the door value, even if it's negative. And also the second mistake is that this should be a plus. So we're going to change that everywhere. Same here, this should be a plus for a door. and we're still gonna update the reward, like that, nums 2 of k. But looking at it, I think in every case we are updating the reward. So maybe maybe we can just say that at the very end, right? Because in the if case or in the else case, we both update the reward. So uh, 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 and the reward doesn't affect anything inside the if loop for this iteration. So we can just move it outside of here, right? And then we're gonna say whether at a door or treasure chest update current reward. Yeah, because you're gonna do that anyway. You can't escape that. So we're gonna just delete all that and say that here. Uh, and delete that line. And then after adding the reward there, we then do the k plus or k minus in there. Yeah, I think this is like a better version of it. And now we're just gonna restart the kernel and apply our debugger. But let's just first run it once. Okay, we're gonna just first run it once. Look at the solution. Um, okay, so this is not correct. It becomes 7. So it's less than what we expected. Now I'm going to again put some breakpoints at places where needed. The first place where we need a breakpoint is, of course, right after the money in the bank calculation here. And then we're gonna break at here before the current reward and that. And we're gonna put another breakpoint here. I mean, right now this is super slow for some reason, but we'll get through it and we'll fix my computer later. Now, after the money in the bank calculation, we're at money in the bank 14, which is correct, and KCW 4, KCW 6, that seems to be correct. And then let's move on to the next breakpoint, which is right after we calculated. I don't know why it's still here. I don't know why. I mean, did it not calculate anything in here? That's impossible, right? But somehow I have to click that play button twice to move it forward. All right, so we are here, and basically what we are doing here is like um, after we just tried the counterclockwise value list, it's still a length of 1, and accumulatively it has also like this -9 and 1. I mean, if we're going first clockwise and then going clockwise from the money in the bank here and then moving on to see what's the door value here, then for this door for this -9 door here at at k equal to 3, right? at k equal to uh, wait, clockwise. Our k clockwise is 4, so it's your, right, we need to look at nums list too, right? At index 4, we have a value of -9. So, and then we have a value of 9, and then we have a value of -7. For -9 value here, we see that, yeah, um, right. So after sweeping from 4 to 6, we somehow still have just one value in here, and that value is -9. I mean, -9, it, it makes sense, right? Because um, our current reward was like 0 to begin with, and then if you just take into account the door cost, it's -9. So there's nothing to complain about that. But it's just that I don't know why when k equals to 6, this update didn't really work. Like it didn't really add another value to VCCW, right? That's what I'm worried about, right? So I'm going to restart the kernel, and then I'm just going to put a breakpoint um, right inside this for loop here. During the, yeah, at 97. And then we're going to see why when k equal to 6, um, that second door wasn't added into the array. So now we're at k equal to 4. So this is like the first door value, and we are appending it. So let's take a look. Now this list, right now it's empty, and the cumulative list is also empty. So once we perform this one step, we're going to have one element in both of these lists, and it's going to be -9 and -9. Oh, not yet the cumulative one, but yeah, let's just step forward again, right? Or just do the play button so that we jump to k equal to 5 now. So once k equal to 5, we've finished everything on k equal to 6, and you see we have one value here and one value here as well. So that is healthy. Um, and our current reward is -9. I believe when we click that again, the current reward will become 0 because we have just taken another um, value chest. I don't know what's going on. Like it just ended. Wow. Really? This is really, really weird. How did it just end? I mean, it's like it didn't even go to the... Ah, I see. Because, right, my bad. For range, for the second input, you always have to add a +1 to it, right? So we have to be super careful, to get used to the range function here. And if we're doing -1, we definitely have to -1 in there. Okay. So sorry about that. Let's just see. what do we get? Yeah, now we're here. Let's just, reuse the debugger. Now we're at k equal to 4. After clicking this button, we should have k equal to 5, and our current gain, current max, current reward should be still -9. But when we click that again, we should be at k equal to 6, right? And our current reward is going to be 0. And right now our CCW list is like one element, but when we step forward a few steps, we should have now first VCCW is updated. It should have two elements in it now. One is like -9, the other one is -7. Does that make sense? Uh, um, so the CCW reward. So for the first reward of visiting it, the the value of visiting the store uh, in a counterclockwise way uh, uh, um, in a counterclockwise way mm, is of course -9. But the value of visiting this door in a counterclockwise way is gonna be -7 plus 9. Mm, I'm thinking it should be 2, right? I'm thinking it should be 2 because, yeah, you don't have to visit this door at all. Uh, Cumulative value. Because you're visiting the door in a counterclockwise fashion, let's just take a look at the original nums2 list, right? If you're visiting this door in a counterclockwise fashion, for this -9 door, of course, the value is -9 because there's no uh, unexplored treasure chest behind it. But if you actually open door number 7, open door marked with -7 there, you can get some reward there, which is 9. So that should boost up your value of visiting that to be +2, right? So I think I think we need a current reward reset somewhere. So after we visit a door uh, uh, somewhere, we need to reset our current reward. Yeah, because what stays, in one um, value chest or treasure chest stays in that value chest. Okay. So definitely, I don't want to let the current reward in one treasure chest to affect the other. So, I mean, if we're already at the door, before we do anything, right, we're going to reset current reward to 0 after uh, 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 after opening it, after before moving on, right? Because the next one is going to be a reward or anything, either a reward or like a door. I don't care, but we gotta reset this because it's already claimed, right? This is something already claimed. Uh, right, so we're gonna reset the reward. Yeah, same thing here. Uh, After we, for example, open a door, we need to reset the reward. Same thing here. So try that. It's still wrong. So let's just reset the kernel and clear the outputs, and um, we know where to look for to debug. So let's just get into it. K in range. Let's see, K in range. No, that's not where we stop. We should stop. So the money in the bank was good. Uh, um, this value thing is where things start to get. This is where things start to get incorrect. So I'll just put a breakpoint right there, and I'm gonna put a breakpoint uh, uh, right in here as well. Come on, right, and then we're gonna start debugging. All right, we're at that same place again. Um, of k equal to 4, right? Because if we look at our nums2 list, the modified list, k equal to 4 means we're at that -9 door there. Uh, and after we run this loop, we would have just reset the current reward, but we've also already added the reward of -9 into our counterclockwise list in there. Yeah, and our current reward, why is it not reset? That's strange, you know? Current re cur reward. It's the same variable, isn't it? Why is it still -9? Oh, because you're doing that update here. So definitely we shouldn't do that. I mean, yeah, this update is the culprit. I mean, we just want the reward to be local. We don't want the reward to start from the very beginning of the first door. We want the reward to be local between doors, right? Yeah, we want them to be local between doors. So definitely this is something wrong. We don't want this uh, uh, to start accumulating. We only want to accumulate the reward value when we are at a reward, right? We only want to accumulate the reward, start accumulating the reward when we're actually at a treasure chest. And after each visiting a door, we just reset, the current reward to 0. And then when we're visiting like treasure chests, uh, we're gonna update the reward with that treasure chest, right? So we do need that else condition here. I was wrong to say that we don't need it. You know, at at the treasure chest, we're going to update current reward. Yeah, that's what we do. And when it's like a door, we also update the current reward, but we just update it with the 0, like that. Yeah, we're gonna do the same just here. Yep. And I think that is probably gonna at least fix this problem that we're dealing with. Right, it's still not correct. Let's just restart the kernel, and then keep debugging. Right, so we're gonna put our breakpoint at the same place on line 97. And then we're gonna just keep going at it. Right, so at this point, if we take a look at our num2 list, we're having something. We're at index 4 minus 9, so we're at the first door of minus 9 here. And if we just click the run button, we should see that our current reward is reset to 0 for the next loop, but we have already memorized a reward of minus 9 into our uh, both in the current uh, in the value list and in the accumulated value list. And once we run the play button again, we should be seeing that now we have a positive reward because we have traveled through a treasure chest of 9. So the current reward is 9. And these lists should stay the same, right? Yeah. And I think we're just going to step through that and see what happens in the last step. Because right now we're at step 6, which is the second door with the door value of minus no with the value of minus 7, but the door value uh, is different. So the door value is going to be the current reward, right? Current reward is like 9 plus nums2, and we're going to append that. And after that, I think that the door value counterclockwise would become 2, the second door. Yeah. Uh, it'll be 2. Yep. And then now we're going to reset the current reward, which is fine because now we have went past another door. And then let's do the accumulative. So we're going to append that accumulative with the value here. And because the previous value was minus 9, I believe, and the current value is what? The current value is 2. So it'll be minus 9 plus 2, which makes sense because it's like minus 9 plus 2. Well, you know what? You shouldn't be accumulating. You really shouldn't be accumulating, I guess, this very last value because this is like the door that you never actually kick open, right? You really never kick open this door. So that's the problem here with the calculation. I mean, the algorithm is doing what I intended to do, but my intention was wrong. I really shouldn't be kicking open the last door at all. I mean, kicking open this last door in the counterclockwise direction. So uh, uh, um, when we are appending those values, right, this means that we're actually doing that accumulative action in the wrong direction. Because when you're going forward, actually, you need to accumulate backward. Okay, you need to accumulate backward. So, so yeah, you need to accumulate backward. So I'm accumulating in the wrong direction. That's what I'm saying. Yeah. I guess, yeah, I guess that's the problem. We're accumulating in the wrong direction. So let's just delete all the accumulation steps, right? All the lines um, uh, that actually accumulates uh, that array, and and right, and we're going to accumulate it afterwards. So, for example, after this for loop going in clockwise to actually collect, the door values in counterclockwise fashion, we have now achieved the counterclockwise array. And if we want to, I guess, keep accumulating the value um, in the counterclockwise fashion, um, do we have like CumSum, Python CumSum? NumPy has a CumSum, all right? So for us, if we don't have a CumSum function, available at our hand, we are going to hand code that CumSum. And we're going to use a for loop to do that. And because now we're traveling for the counterclockwise accumulation, right? We need to go actually from the last element, from the last door all the way down to the first door. So it's actually in a um, completely different direction. So we're actually going from KCCW. No, um, endorse. All right, K plus one and endorse, right? Plus equal to one, right? So no, this is where we have a door. Yeah. So that's how many doors we have. And now we have the number of doors. So it'll be indoors minus one down to whatever. Uh, um, Definitely not zero, so it's minus one, right? Minus one. Right in that range. Uh, right. Mm, right. And we're going to say that accumulate, right? V CW CCW accumulate equals to uh, uh, um, backward direction. This equals to mm, actually we're gonna append, right? Yeah. Um, I mean, if we already know the length of it, we don't really need to initialize them like that in here. We can just say this is gonna be none times what endorse. Yeah. So we can make it just a list, and then K, the first door, is just the value itself, VCCW of that itself. Um, well, actually, zeros, right? Let's make zero, and then right, it'll be uh, what um, um, let's see. Right, the first one, it'll just be the the door value itself. The second one, the second door's accumulated value is going to be the first door's value plus the second door's value. Right, so we just need an iterator, basically. Like a temp. Yeah, let's just like a temp. It'll be a temp plus that, and then we're gonna say temp is going to be this, right? So this is how you accumulate it. You first um, use temp and then plus this value here, and you're gonna assign temp this value. So the next time when you call temp, it becomes uh, um, a value at the previous step, right? Right. And then we don't really need to flip it because we just need the maximum value out of it, right? So we're going to calculate, in this case, calculate VCW in forward direction. Is that right? Because when we're accumulating in a forward direction, we're doing that in a forward direction. Yes. So we're gonna do clockwise accumulation is 0 times indoors and temp equal to 0, and we're doing it in a forward direction, so um, start from 0 and then we end at indoors and then with an increment of 1, and then VC accum equals to temp plus VCK. uh, Wait, hold on, just hold on. I think when you were doing the when you were doing that, like doing the clockwise accumulation, you, the way you built them backwards. You see, you built them backwards. Um, so the first element in this array here, in this VCW array here, is actually um, the last one. Is that right? Because you're going from, the largest index down. It is true. So again, to do it in the forward direction, you still need to do the same thing because it was reversed here in the first place. So in order to do it in the forward direction, you have to reverse it back, right? Because VCW was collected in a backward direction. We have to use backward indexing again in order to bring it back to the forward direction. So Um, we're taking the last one in that list, right? And then the first one would be endorse -1. I'm gonna use a temp. Wait, hold on. Hold on. It's still not right. I mean, we're accumulating the backward direction, but we really want to fill it up in a forward direction, right? Mm, I mean, that's fine. That's fine. Endorse, fine. That's fine. I mean, the final order in this array doesn't really matter because we're just using maximum in it. So I guess in the end it doesn't matter, right? So that's about it. And let's see. Okay, now it's actually giving us the right answer. I'm not going to be picky out about the details. I'm just going to look at this, and it seems to be working. Now we can officially remove this part because it was a mistake. And this one here is our new baby, and let's submit it for scoring. Run the code. Whoa, wrong answer. Because we are returning too many things in the first function here. We really don't need everything. We just need this. So in that first function, we don't want to return so many things. We just want to return that. Let's run the code. Correct answer, 17 millisecond, 46 millisecond. A little expensive. Again, a wrong answer. All right. But this is actually a new test case, so I'm thinking we're still making progress, right? Like all negative. This is like the all negative case. So for the all negative case, if we're really about to, solve it, okay, this is expecting a -1, right? But what we have is whoa, am I a -2? So we're going to focus on that and work out why it gives a -2. Because, okay, so first of all, our first negative number that we spotted is at index 2, which makes sense. And then after we remove the -1, our classical maximum subarray result is -2, which also makes sense. But then when we, when we run case 2 with, this -1 included um, in our in our case 2 subproblem, then it actually produced -3, which is, kind of weird because our money in the bank, it should be just -1, right? I wanted to see what is wrong in there because I wanted to see what is money in the bank, and I wanted to see what is the rest of it. Like those two doors, they don't really provide any further value, right? So we shouldn't be taking them at all. Right, if those doors they don't provide any value, we don't take them. So I think that's the thing. Like we still took one door. I think we still took one door, like one less damaging door, because maybe we didn't give ourselves the choice to not take any doors, and we need to implement that. I think that's the problem, but let's find out. So we're gonna stop ourselves at the end of money in the bank, right? Yes. So that's at the end of the money in the bank. Um, and then we want to see what are like our arrays for VCW and VCCW. And yeah, and let's take a look. Our money in the bank, it should be just -1. That's correct. So let's just move forward, okay? And we're at this here, and we have these two arrays. Um, the list accumulated a list. So if we, for counterclockwise, mm, counterclockwise, if we take the first door, it'll be a cost of -3. If we take two doors, it'll be a cost of -5. It makes sense. For the clockwise list, it's probably like similar. It'll be a -3 and a -2. How come I think this is a little bit problematic because they should be mirroring each other. Maybe the direction is not right, but it should be mirroring each other, right? Yeah. So when we were calculating our clockwise, I think when we're calculating our clockwise, uh, when we were calculating our clockwise direction, there's something wrong. So for example, let's compare them line to line. For the counterclockwise, it's like CW to CCW plus 1. Uh, for clockwise, it's KCCW down to KCW -1. That is right. And then if condition here, append current reward, number of doors. Yeah, number of doors is fine. We can just use it once there. Um, and then else, right? And then K plus 1, K minus 1. So the calculation for that is correct. And the accumulative, so we're calculating the accumulative, uh, right, accumulative door values here. For the counterclockwise, we're just gonna initialize with n doors, and then we say we travel in the backward direction, because for traveling counterclockwise, we need to start from uh, uh, the last door first. From the last door first, right? Because you're doing it in a counterclockwise direction, you naturally reach the last door first, right? And the index of the last door is n doors -1, and you go down all the way to -1, and then you just accumulate that, and you do the temp, uh, yeah, and then you do the update until you reach k equal to 0, the first door, and then you again update that value with temp plus that. Um, but you just never use the first door if you're going backwards, because the first door is useless. If you open the first door in the backward way and a counterclockwise way, you just get back to your money in the bank. Um, all right, so let's see on the other side if we're doing clockwise door opening. For the clockwise door opening, again, we initialize the doors with n doors, the cumulative array within values, n doors values, temp, and then because we calculated this VCW in a um, in a backward indexing way in the first place, right? Because that is how you can accumulate the reward in the in the correct direction. Um, so when you when you want to accumulate the actual rewards in the forward direction, you have to again use reverse. indexing, use backward indexing. So we're again starting from the last element in the VCW list, because the last element in the VCW list is going to be actually the value of the first door, right? So the first door value is added to the temp, which is 0. And then that's the cumulative value of the first door. And then you decrease this k once more, and it becomes, the cumulative value um, become the second door. And then you add the second door's value to temp, which was like the first door's value. Then you have the cumulative value of opening 2 doors, which makes sense. That mean in this case it's minus 2 plus 4, which is 2 there, and it makes sense. So if we look at our um, arrays, I was thinking, should they be like the same or different? Well, they are different. So okay, they are different because opening door in one direction or the other in the other direction, you really have different values. Okay, fine. You proved the point. I mean, these two arrays, they're not symmetric at all. So, but what about VCW list? Are they symmetric? Minus 2, 4, 0, 5, minus 4. They're not symmetric. So don't worry about them being not symmetric, okay? Um, let's just move on. Wait, we are still having like a minus 2 here? What? I don't know what's happening. Okay, let's stop the debugging. I mean, let's stop the debugging and then just calculate the results. It's a minus 2. I wonder why. Let's just, also return again the k index, uh, and then the max case 1 and the max case 2. This is more helpful. Reach your information. So this is still giving us minus 3. All right. So in that case, we still have some problem here. But we have verified that our, CCW array should be fine. But let's see. Right, we still have this problem to fix. That if we only have like uh, so this is our money in the bank, right? Because everything else are like just doors with no rewards behind them. Then we should give the algorithm the freedom to take no doors. But in this, we're basically saying, hey, those are the values of our doors. You need to at least take one, right? So what we can do to fix that is we're gonna say, hey, um, if we're going like in the forward direction, let's use black, let's use or purple. So if we're going in the forward direction, you have the option of not traveling at all. No doors. ND, right? ND, no doors. And also here you have the option of going nowhere, no doors. So if you're going no doors, you're gonna have a 0, right? So accumulatively as well, you should be given the freedom to compare this to the to compare this with 0, right? Compare this with 0 and take the maximum and take the maximum value. Because if it is the case that all doors are bad, I mean, there's no door that give you any good value, you might as well just take 0, right? So we're gonna do that. Uh, Max of that array and what? Um, We want to add a 0 at the end of those arrays, right? We just need to add a 0 at the end of any array. Plus, this. Yeah, so that's that, yeah, the 0 is the freedom to not take any doors if all the doors are bad, all the door values are bad. There's no are negative, are negative. You need to give yourself the freedom. So let's say we do that again, and there we go. We seem to have the right answer now. 3, 10, minus 2, 8, 18, 16, minus 1. All right, so that's about that. And we never know. I mean, you just never know, okay? You just never know if this is the right answer. We'll just have to run and see. 28 millisecond. Okay, good. Still, there's a wrong answer, but okay, we're gonna work with it. All right. This might be a tricky case that people have trained and realized. But anyway, what are we expecting? We are expecting this answer to be 29. All right, 29. Uh, right, and we can just put back those very good diagnostic indicators in our main function so that while we are outputting these results, we can compare what we are getting wrong. All right. Yeah, let's just kill that. So, right, we have taken index number 7. So 0, 1, 2, 3, 4, 5, 6, 7. Yeah, this minus 5 here. So in our case 1, we have removed our 27th value, and the result is 27. And in the second one, we have worked out, it to be 21. So definitely, it's okay. The problem in the case number 2, because we should be getting a 27 where we actually just got a 21, and I wonder why is that. Let's right, let's take this actually, and then we hand calculate using our heuristic or our algorithm, our door value algorithm here, and see if we can find that problem ourselves, right? So let's move this to there. Let's just hand calculate following our algorithm that we come up with. Okay, so let's just draw the circle. Draw the circle, right? And it's got 1, 2, 3, 4, 5, 6, 7, 8, 9 values, right? And we're gonna do it in a clockwise way to list them down. 5, 6, 1, 4, 8, minus 8, 7, minus 5, 3. So right, those are 1, 2, 3, 4, 5, 6, 7, 8, 9 values. And we decided to actually center ourselves at this point here. So this will become the new first value, right? Because we have shifted our we have shifted our snake heart, so to speak. So this is going to be our snake heart. K equal to 0, snake heart. And now we're going to see what's our money in the bank, right? Let's use a different color to try to calculate our money in the bank. Uh, Again, same color. Uh, this is going to be our color, money in the bank, all the way here. Wow, that's a lot of money in the bank. Actually, yeah, pretty good. So our MITB, it should be, let's see, 7, 2, 5, 10, 16, 17, 21, 29. So our money in the bank is already 29, right? We only have one door. Of course, we mark our doors with purple, but then we can choose not to take the door because there's nothing behind it, right? So we should get a 29, but somehow it didn't get there. So I think our algorithm is still correct. It's just that I didn't. There's some implementation error down the line here. So we're gonna start the debugger and get into our um, function and then see if our money in the bank was correct. That's the first step that I want to take. Right? It's the first thing I want to see if the money in the bank is correct. We're expecting the money in the bank to be 29. Well, okay. I guess we need to restart the kernel first to enable the debugger. All right, let's start the debugger again. Put our breakpoint at right before step 2 so that we can take a look at our money in the bank. Because I'm worried that, money in the bank is what's incorrect. Why didn't we even go to the money in the bank? That's weird. Is it because that we actually, you know, went through this? Yeah, let's actually try that. Right. CW and CCW. Right, this is the case. Like these two indices overlap. If they overlap, it means all values are money in the bank. But I mean, it's not the case, right? We still have one index there. So let's just, highlight our indices and to make sure that our indices are not, done wrong. So this is like indices 0, right? This is 1, 2, 3, 4, 5, 6, 7, 8. And um, let's take a look at our, you know, clockwise and counterclockwise money in the bank indices. So, I mean, at the end of the while loop, so for the last element for the money in the bank, we're still going to increase or decrease the counterclockwise and clockwise index by 1. So there's a possibility that, if there's only one door left, those things, they actually collide, right? So, for example, I'm just going to follow this thing line by line here. So when we were first doing it clockwise, we are increasing our KCW, and the last money in the bank in the clockwise direction is this one. But at the end of it, we still increased our CCW. So at the end, our KCW is 7. In the same way, you know, although our last money in the bank in the counterclockwise way um, is like this index number 8, but we still at our last moment, moved our k, k c k c c w again, decreased it by 1, so we were pointing at the same location here. So it creates like a false impression for the algorithm to think that we actually overlapped, right? So for these things to actually overlap, I think it has to be not like a greater or equal to 0. It has to be a greater than 0. Yeah, at least greater than 0. Actually, to be strictly overlapping, it has to be like greater um, greater than 0, and it should be greater or equal to that plus 2, right? Or greater than that plus 1. Yeah, this is how an actual overlap happens. Right. So let's just turn off the debugger. See if this is giving us 29. Okay, it's giving us 29. What about the other test cases? 3, 10, minus 2, 8, 18, 16, minus 1, 29. Okay, so seems like this is now correct, and we can submit it again to LeetCode. And we're gonna just in the main function here, remove those diagnostic outputs. And let's run the code here. 21 milliseconds. Run these things 20 milliseconds, looking good. Okay, still a wrong answer. Wow. This is a really hard problem, huh? I mean, guys, this is like, I don't know, really tricky. Now we're just gonna, put that test case here. And we're going to work with this test case. And what is the expected answer again? The expected answer is uh, um, 99 instead of 90. So expecting 99. Right. So let's see. All right. So we took like the 27 out, which is like the first negative value that we encounter, right? Makes sense. It's a minus 12. And of course, removing that, you're going to get a suboptimal result of 83. So the optimal solution should be the one with the case 2 with this value as the snake body, the snake heart. So we're again going into the going in there. But how about let's just hand calculate this on this test case again uh, with hand, because that is a really good opportunity for us to really verify things. So I think there's like 27, 20, 29 values, right? 29 values. We're gonna do that anyway. So uh, yeah, it's gonna be a pretty long, pretty big circle. Do we have like lines, paths? Yeah, we can have paths. I didn't know we can do that. So if we can have a path like this, so we might as well just use it to draw circles, right? Oops, it's a straight path. Why don't we line, stamp, web, eraser, uh, path line, path, right. Okay, how did I do that? How did I do what? Oh, that's how you do it. Okay. Right, so let's just draw a circle in this way. Right, and what? Like this. That's a little weird, but I mean, we can still handle it. Okay. You know what? Yeah, it's good enough, all right? It's good enough. Not the best circle in my life, but it's good enough. And let's just switch to a pencil. Right. Now let's just draw that. Well, actually, we should use black, right? Just to be consistent with our colors, we should use the black thing. So let's use the path, but use the black here. And 1 point. Uh, you know what? Maybe we just do some anchor point here and there until we got like a nearly round circle, and then we can just readjust the details, the micro details later. Well, it's not really as good as me just drawing a circle myself, all right? This is like actually more ugly. It's like a pancake that was done bad. Um, anyway, I'm just gonna use a hand pencil, right? And then we're just gonna draw this circle with hand. Right, look at that, not bad, right? Uh, and then of course we found our first index to be minus 12, so that's where we're gonna start, right? In uh, yeah, minus 12. Let's start drawing, writing these values down. Uh, Minus 12 is gonna be our first value, and then 22. Is that is that true? Because I think because I would want minus 12 to be, yeah, let's see, almost forgot our convention. So our minus 5 is the first one, and then we do like 3, 5, 6, 1. Is that how we do it? Let's just confirm with this next one here. Minus 2, 0, 7, 5. Right, right. That's how we do it. So minus 12, and then we're just going to shift forward 22, 16, and then minus 9, 14, 24, minus 14, 12, 18, minus 18, minus 10, another minus 10, minus 23, minus 2, minus 23 again, 11, 12, 18, uh, minus 9, 9, minus 29, 12, 4, minus 8, 15, 11, minus 12, minus 16, minus 9, 19, and finally we arrive at 12. Yes. All right, that's pretty good. Now we are going to use this orange color and then try to illustrate what is the money in our bank, right? This is where we start, and money in our bank is this, and in this direction it's just this. So it's not a lot, but it's that's our money in the bank. Um, so MITB equals to 19 minus 12, so that's 7, 29, 45. So our money in the bank should be 45. That's the first thing to check, right? And then, of course, we're gonna mark those doors, right, with our purple markers. So every negative value is a door. Door there, door there, door, 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 door there, another door, 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 door. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? 14 doors. So um, we can just, make a list of our door values naturally in here. It's going to be, right, so our V clockwise, and then um, it'll be, door 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 doors. Then, right, we're gonna, let's see, let's do it in terms of, let's see if we can change the workspace and, yeah, alignment to the left. CW, V, CCW, right, something like that. Um, yep. So we have that, and of course later on we're gonna have our VCW accumulated, VCCW accumulated, right? Things like that. Oops. Right. So we're gonna fill this chart here and find out what went wrong with our solution. The first thing, of course, to check is to check if the money in the bank is the same as what I calculated. So I'm gonna put a breakpoint again right after the money in the bank calculation, right here, right, and then we're gonna run it, and we're gonna run this. Our money in the bank 45, so that was actually correct. So then the next thing to calculate in our algorithm are those VCW and VCCW values. I'm going to put another breakpoint there and then move on. First to see is to see actually how many doors do we have there. Number of doors 14, that's correct, right? And we want to take a look at our VCCW list. That's a pretty long list, and let's just see if that matches what we expect. Okay. We're gonna group our treasure chest a little bit first. So our treasure chest, for example, this is we can combine uh, we can combine those treasure chests that are next to each other. So this is 26. Um, these two they worth like 16. 16. This one is a 9, and these two, oh, these three actually. So it's 30, 41. That's a pretty big package. Uh, and then we have this one here as well. That's a 30. And we have these two here, and I believe that is 38, right? So we can start writing these values down. But before we do that, I think we need to expand this a little bit because we don't have enough space for them. We're not gonna have enough space for them. Um, so, all right, that was a phone call, and I'm back. So let's just you know, make sure we got this right. Um, we need to just write those things down in a correct way. And let's see. If we start with um, VCCW, because that's what we're calculating first, right? Yeah, VCCW, that's what we're calculating first. So let's see. If we travel, in the backward, for the breaking doors, open doors in the backward counterclockwise direction, what is the value of opening the first door here? Uh, in a backward, I mean the last door here in the backward order. It is, you know, for that one, number 14, number 14, right? Um, the value is -9. It's not really a lot of value. And then the next one is what, -16 as well, right? And then the next one is -12, not a lot of value. And the next one, well, breaking the next one is pretty lucrative because you're gonna get 26. Wait, hold on. Let me just be sure that we're matching indices right. So we have, let's just mark these doors 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we don't really have a 14 there. That's the first mistake I made. So there's no 14 there, right? Right, there's no 14 there to begin with. Um, but at 13 we have a value of 9, and at 12 we have a value of 16. Um, you know what? I'm just gonna, instead of typing like this, I'm just gonna use drawing. I think using drawing is easier this time for me. So yeah, I'm just gonna use the drawing. Pencil, yes. Um, yep, and then outline. Yeah, the same outline. So VCCW, right? The first one is what? -9. Here. Let's just draw a line here. So this is -9. This is -16. This is actually, this one is actually pretty lucrative this one is minus 12, but after you crack the door open, you're gonna see 26. So it should be plus 14 here. And then the next one, it would be what? Yeah, we also have some reward afterwards. We have a minus 8 and then we have a 16. So the reward is 8. For the next door at 9, the cost is 29, but we can get a reward of 9, so minus 20. At 8, um, we have a total huge reward of 41, but the cost is minus 9, so the overall reward is 32. Um, for door number 7, it's all cost, no gains, minus 23. For door 6, minus 2, nothing behind it. For door 5, it's minus 23 again, nothing behind it. For door number 4, minus 10. For door number 3, minus 10. For door number 2, minus, wait, for door minus 10, we do have something. For door minus 2, we have a 30 in reward and a minus 18 in cost. So overall, we're going to have a gain of 12. For door number 1, we have a reward of 38 and a cost of 14. So we're going to get 24 in reward. Right. So for door 0, whatever it is, there's no reward after it. So it's all cost by itself. Right, so that is our list of VCCW. Let's see if it's actually what we see here. So first one, minus 9. Yeah, minus 9, 24, 12, 24, 12, minus 10, 2 minus 10s, and minus 23, minus 2, minus 23, minus 22, minus 2, minus 23, right, and then 32 minus 28, 32 minus 28, right, and the last three, 14 minus 16 minus 9, 14 minus 16 minus 9, right, so this is correct. Um, and if that is correct, I believe, right, we also have this cumulative sum. Do we want to check that? We do. So VCCW accumulative, let's just calculate in our hand as well, right? Let's just first hand calculate that. Right. We want somehow like a straight, more or less straight line drawn here. And because it's like backward, so we're gonna have to accumulate it from backward, right? So minus 9, and then if you add those two up, minus 25. If you add the three of them up, you just add 14 to minus 25, you get what, minus 11. And then you add 8 to it, you have minus 3, and minus 20, minus 23, and then this 32 added to it. Wow, we turned positive with that big reward. Becomes 9. Then we have another minus 23 here, and it's going to bring us down to minus 14, right? Right. And then with that minus 2, this becomes further negative minus 16. And then minus 23, that's going to bring us down to minus 39. There's not really much value down that route. Okay, so another minus 10, minus 49, there you go. Another minus 10, minus 59. Wow, deep in that. Um, let's see, 12, okay. Back a little bit. Now we're at minus 47. And the next one, uh, 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 is 24. So this is a pretty big bump. Now we're at minus 23, um, right? Right. And then with that minus 9, finally this becomes, well, the last one you don't really need to calculate, but I'm going to calculate it anyway. It's going to be minus 32. So let's compare that with what we have. Right, if the last value is correct, you can bet that, everything's correct. But I'm just going to verify the first five, okay? Minus 32, minus 23, minus 47, minus 59, minus 49, 30, 47, 49, 50, 49. Yep. So this is verified. So let's just go to the next couple of lines for the forward calculation. Well, let's see. Right, so I'm going to put another breakpoint there and then click the play button. So it'll be at this point. And then we're going to check VCW list as well as the VCW accumulation list. Let's start with the VCW list. Again, we're counting again. Now, if we go positive, right, the value of the first door at 0, door 0, the value of this door is minus 9 because, wait, it is not. Careful. We actually have something behind the store. So there's 38 reward, pretty big. And the cost is minus 9. So overall, we're still going to get 29 out of it, right? And then for door 1, um, that's a lot of reward as well. It's 30, but the cost is minus 14. So we have a reward of overall 16. Um, door number 2, no reward, just cost. So it's minus 18. Number 3, the same thing, minus 10. Number 4, same thing, minus 10. Door 5, same thing, minus 23. Door 6, same thing, minus 2. Door 7, well, there's something behind, 41, the largest sum of reward there. The cost is 23 though, so you're gonna get a 18 out of it. Yeah, you're gonna get an 18 out of it. And door number 8, reward 9, cost 9, so cancels out. Um, door number 9, 16 reward, minus 29 cost. So overall, you're going to have a cost of minus 13, right? Let's just write that. And then door number 10, you have a reward of 26, cost of 8. So overall, you're going to have a reward of 18. Um, door number 11, it's just a door, nothing behind. So the cost is minus 12. Door number 12, it's just a door. Door number 13, it's just a door because behind it is what we have money in the bank. So now let's just compare what we have here with what our algorithm has computed for us. 2916 minus 18. Well, yeah, we should count it like, yeah, in the reverse order. We know this. 2916 minus 18, right? And then minus 10, minus 10, minus 23, minus 10, minus 10, minus 23, and then minus 2, 18, 0, minus 2, 18, 0, that's right. Minus 13, 18, minus 12, minus 13, 18, minus 12, that's correct. Minus 16, minus 9. Right, this is correct. But now we're going to verify the next crucial array, which is this, VCW accumulated in the clockwise direction. So we're going to start counting from the door value of the first door. at index 0. So it's 29 to start to begin with. And then 29 plus 16, that's a pretty big sum. So it's like what, 45? Yeah, 45 here. And then minus 18, that'll be 27. Yeah, down to 27. Minus 10, that becomes 17. Another minus 10 becomes 7. Minus 23, we're down to minus 16. Yeah, right. Because um, minus 23 plus 7. Wait a second. Yeah, it is. It is minus 16. And then minus 2, we plus that, it becomes minus 18. Um, and then minus 18 plus 18, it becomes 0. 0 plus 0, again 0. Plus minus 13 plus 18, that becomes 5. Plus minus 12, that becomes minus 7. Minus 16, that becomes minus 23. Minus 9, that becomes minus 32. Okay, so let's read the list. Of course, it's again going to be in reverse order. Minus 32, minus 27, minus 7, minus 32, minus 27, minus 7. As long as the last few is correct, usually it's correct, but I'm just going to verify everything just to be sure. 5 minus 13, 0, 0. 5 minus 13, 0, 0, right? And then minus 18, minus 16, 7, 17, 27. Minus 18, minus 16, 7, 17, 27, and then 45, 29. And then 45, 29. Right, so that is also correct. So how come like our money in the bank is correct, and then those things are correct? So you're saying that the maximum that you can get, right, is the maximum we can get, right? Now, here comes the critical moment. Our best reward. It could be, it's money in the bank, right? Money in the bank plus whatever is maximal uh, in those two lines, in those two lists, um, including a 0, right? If there's no larger value. So we're looking at this 45 right here. This is like the largest among these things here. So money in the bank plus, yeah, like the max of VCW AC, VCCW AC, and 0. And this is 45 plus 45, and it becomes 90. So our algorithm was actually okay. I mean, there's nothing wrong with it, right? So when you go ahead and say that's what we have, then you return 90. But then we were expecting 99. That means our algorithm was wrong, right? That means our algorithm was wrong. How? I just don't know how. Like, is there like an even better way of taking it? Well, let's just see where this is, okay? This is like going clockwise and take the first two doors, right? Going clockwise, take the first door, take the second door, and we stop there. Right. And do we take any doors? Do we take any doors down this line? Wait, hold on. Wait. I think Oh, right, right. This expression was wrong because, I mean, we traveled this far in a clockwise direction, right? But we can still travel far, like, yeah. So this is how much we traveled in the forward direction, and this is where we want to go, and that is fine. But we still can also travel in the backward direction, and we can get something good either as well. Like we can get as much as 9 here by traveling back, and you should take that 9 as well. You shouldn't ignore it, right? So as long as this whatever this index and this index they don't overlap, you're good, right? Right, right. So that's actually an algorithmic error that we're making here. So what is the algorithmic fix that we need to do here? Um, so this is definitely wrong. Not take the larger maximum. Um, it is to compare. We need to compare the ending indices of the most lucrative. We need to compare the ending indices of the most lucrative uh, um, mm, I guess clockwise and counterclockwise um, uh, searches, right? Um, check if they overlap, right? And if they do not overlap, we're gonna add the best of both worlds, add the best of both CW and CCW accumulative values uh, um, um, to the MITB, right? So the to the money in the bank. So definitely it's going to be like that, and um, then it'll become like max this plus max this, uh, right? And if we add those two integer values, um, then what if those two integer values are still less than 0? I mean, we're going to take this plus like a 0, right? And then we're going to take this plus a 0 because we're going to give the freedom in each directions. The 0 is the freedom to not uh, open any doors in either direction. Yeah, I'm going to take the maximum of that and plus the maximum of that. That is if like there's no overlap. But can they actually overlap? Do we have like an overlap case? I think we didn't have an overlap here, right? We did have an overlap here. Um, well, well, yeah, we did have like an overlap here because, uh, right, you see, we did have an overlap here. The best value here is to do this, and the best value here is to do this. So there was an overlap. So what do we do with that overlap? Mm, well, if we have these overlaps here, then we have to negotiate, right? Negotiate in the overlapping region like we're gonna add them up and see which one has the better sum. So for example, we're gonna determine for door number 2, do we open it on the left or on the right? Like what is the last door that we open um, on the left if we do have overlap, right? For example, yeah, check if we're gonna check the maximum index. Um, how do we compare those? Well, yeah, we can find the maximum there, and we can find the maximum here. And what if we just, try it on one row? Let's say we can either not open the door, or we can, open this door and then leave, these doors for the for the counterclockwise direction, or we can open this door on the left and then leave the rest for the counterclockwise direction. It's gonna be better. Or yeah, I mean, we want the accumulated results, right? So it's gonna be like we can take this, or we can take this and we leave the other doors to the other direction. So this plus the maximum of the other direction, it will be uh, 1 plus minus 2, so it's a minus 1. And if we take this door opened on the clockwise direction and we take this door on the counterclockwise direction, we're going to do a 3. And if we did do this and we're going to let counterclockwise to take 0, which is like trivial, we're going to have 2. But if we take 7 on the clockwise direction, and we can take a 0 in this direction, right? And then the maximum gain here is a 7 here by opening doors. Right, so definitely there is a region of negotiation. So definitely there is like a region of negotiation. In this region of a negotiation, we're going to negotiate which one is going to be better. Like take this or take this, um, and then the other one has to set has to step back. Um, but this computation it seems like it's going to cost us another uh, O of n squared in terms of computation, right? We don't want it to scale to O n squared for this kind of computation. So how about we pre-calculate? Pre-calculate what? Um, pre-calculate um, the maximum that you can ever achieve up till a certain point, right? Yeah, okay. We need another array to represent, the maximum possible the maximum possible array from one direction. Yeah, right. I guess we have to. I mean, it does get this complicated in the end. So we're going to let's say we're going to take this example, right? We're going to take this example, and then we're going to basically use this example and then expand it. Let's take this out and just filling in what's missing here. And this masking, that's simply not right. Like versus 0, I know, but right now we just need another array. So this, let's just leave it there. 5 doors. We need to create another array. And the array is going to be called vccw cw uh, 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 accumulated um, max, right? Accumulated max, and then vccw accumulated max. The name is like a little bit confusing, I know, but you'll see what it means. Um, and I think it does make sense to include them here. Let me just illustrate what I mean here. Now, because there's conflict, right? There is conflict between in this zone when there's overlap. So in that case, we're going to build um, another set of value, right? So for ACC max in the clockwise direction, um, this one is still going to be 2, minus 2. But then once we get into like a 2 here, we're going to update it with the maximum value. And if it's 2 here, maximum value. And it's a 7 here, it's maximum value. When it's a 3 there, I mean, we're going to update it with the maximum value. So it's ascending in this direction. Same for the CCW accumulation, but we're going to do it from the last index. So minus 2, 0, 1, 1, 1. Right. So we have this, and now we can now like just basically create another, overall array, overall value, v overall combined, or just v combined, right? Yeah, just call it v combined. And what it is it's going to, it is going to first take the reference of this first array, uh, and then look at the value below as well. Just basically summing them up. So minus 2 plus 1, that's a minus 1, right? Oh, actually, uh, it should be looking at this plus this, and it gets to this minus 1. Um, and then for this one here, we need to look at, the 2 here, uh, and then the 1 here. So this creates a 3 here. And then we're going to look at a 2 here and a 0 here, and it creates a 2 here. Um, Actually, we will never have minus 2's because, before that we had a 0, right? So if we don't take any values, we're going to have a 0. So yeah, if we don't take any doors, we're going to have a value of 0 here. So those values are wrong, and I'm going to say this first value is going to be 0. Whoops. This first value is going to be 0 here because we have to take into account that. And then 0, 2, 2, 7, 7. And this is going to be 0 because we have a 0 there. 0, 0, 1, 1, 1. Yeah. So 0, 1, Now this is going to be plus. Yeah, these values are incorrect. I'm going to redo them, redo all of them. Um, right. Now this is 0 plus 1, it's 1. 2 plus 1, it's 3. 2 plus 0, that is a 2. 7 plus 0 here, it is a 7, right? Uh, and because we never take this, so um, we never take that. So I guess then if we don't take anything here, so for the last door, it is only up to, whether we are going to open the last door or not. So uh, um, I mean, the last door, we're gonna do a 0 here because we never opened that door, right? And then yeah, and then yeah, it'll be like that. And this actually, we never take this as well. So just so you know, it's gonna be like that. And maximum is of course this one here. Uh, and we're just gonna take this. And what is the value of this array? It's called v max combined. V combined, right? Yep, that's how we're gonna name it, and that's how we're gonna calculate it. And we need to include this array when there's like conflict. I mean, when there's no conflict, um, we may as well calculate it because in this way we don't have to run the max function here anymore, right? So we're going to um, combine vcwaq and vccwaq into a combined array, combined list, v combined, uh, uh, taking into account the overlap cases. Right. So taking into account the overlap cases, and this is how we're gonna define our that we combine, right? So in terms of the equation, we're just gonna write v combined. It equals to VCC, VCW, ACC max, uh, um, right? And then right, we need to first calculate those maxes, and then we just add them up, right? No, we add um, the shifted the shifted version of them together. We add the shifted version of them together. So we're gonna add VCCW ACC max shifted, right? Yep. So what is the shifted array then? So the shifted array, if you're interested, it's gonna be this, and then what is the next value? Um, doesn't matter because the v combined here, the last one here, um, it is definitely it definitely means that, we're not opening, because it's impossible that we open that door. We open that door in the clockwise direction, the last door. So the last door then has to be either opened or not opened by the by the last, by the last element, right? So because this one means that we're gonna open the second to last door on in the clockwise direction, and the next one would mean what? We're gonna open up the door in the counterclockwise direction, open the last door in the clockwise direction as well. Uh, that's definitely not optimal, right? Because the only choices are like whether we open the first door. There are only four choices, right? So it's going to be either we open, um, because the first door we never open it from the counterclockwise direction as well. So the first door, the only thing we do is we either we either open it from the clockwise direction, or we just don't. We just leave it unopened, right? Right. So you need to remember that this is like a special case here, and this is a special case here. And we are just adding the shifted version of it to get something here. So for this 0, we can just consider um, this to be what? To be none, right? And then yeah, this is also something like a none. And then we just, shift it and we add it up. None and none, but um, the value of this is at least 0, right? So this value, I mean, this value is not important. So let's just, cut all of these things out. I mean, this last value is not really important. So we're going to just consider, right, consider these values added, shifted. And so basically we're not going to talk about these these values. These are like garbage. We're going to just throw them away. Uh, and So although there are like 5 doors, in the end we're just gonna have 4 choices, and we're gonna take the max in that 4 choices. Yeah. Um, so this element, is gonna be have a 4 element. These things have like 4 elements, right? So that they have 1 element less than the number of doors, and then it's equal to this thing shifted, right? And that's what we're gonna implement in our code. So we first need to establish this VCWACC max, and it is going to be um, VCWACC max. Well, excuse me. We know that it is in the wrong order, so this is where we actually flip it back, right? This is where we flip it back, uh, and then starting from the last value, and then down to the first value, using this. And that's how we flip it, right? Flip VCW cum into the right order, into the correct order, uh, correct door order, you know. Yep, we're gonna flip it into the correct door order, and then ACC max. Right, we're gonna just create those things like this in range of indoors -1. Yeah, just range indoors. Yeah, these arrays, these lists are naturally one element less than indoors. Right, and then we're gonna do this of k, right? We're gonna initialize it first. Uh, let's say 0 times n indoors -1, and then another one would be counterclockwise as well. This one here, this one we're gonna do it in a clockwise way, right? So it's gonna be like a max between um, a 0 array plus what we have VCW accumulated from the beginning to k. So for example, when k is equal to 0, it's just gonna be 0 to 0, right? Yep. And right, and when k equal to 1, it's gonna be the first two in the accumulated list, and then between that and the and 0, whichever is larger, um, endorse -1. Well, wait a second. Um, we should do endorse -1 here. Yeah, right. And also for the other one for k in range, um, uh, um, endorse -2 all the way down to 0, right? Um, so for this one here, VCW ACC max of k, uh, this is going to be the cumulative amount of a 0 and also another one, which is VCCW accum, and then we're going to start from the back, right? For this one, we're going to start from the back. Um, right, and we're going to try to find the maximum so far. Maximum so far, so it's going to be accum from, let's see, from the actually the endorse -1 all the way down to down to k, but we're gonna need this, right? K minus 1, minus 1, right? So all the values, maximum. Wait, but then this is gonna be n2. This is bad, right? This is really bad. This is really bad. Yeah, it's really bad. We need a temporal value. We can't afford to use the max function here, because that is going to make this uh, like O of n squared. So definitely we need to let's see, um, we definitely need to recalculate this in accumulated max, right? So for this 0, we computed that as the 0, the maximum between 0 and minus 2, right? So this will be like the maximum between 0 and the first value. So let's just say k, right? Max between these two, and um, is that okay? I mean, yeah, it's just a max between two values. I think we can still afford it. But for the next iteration, we're going to need to calculate this as the max between the current VCW accum value and whatever was previously the maximum. So we're going to store a temp, you know, um, we're going to use a temp to basically store uh, uh, um, the max value from last step, right? And then now we're going to compare that between this and this and this temp value here. 0, current value, or temp. Is that right? Do we have to like always add 0 here? I guess we do. So yeah, and also this one is wrong because max 0 plus vacuum k plus temp. Let's just restart the temp here. We're gonna restart the temp, reset the temp value here as well. Um, we need a temp here as well. CW ACC max. So this temp is gonna remember whatever is the maximum value from last step, and then we're gonna make sure that this is like at least that, and then we're gonna also look at the previous value here. I mean the the current accumulated value here, and I think we don't need to compare 0 at each step. We just need to compare 0 at the first step. We just need to add a 0 in the first step so that we can skip this computation for the remainder of the steps. But that's gonna have to add more lines. Let's just be lazy and not add more lines and just leave it that way. And VCC VCCW, ACC max. We have those, right? And now we have those. We're going to be able to combine. We will be able to create the V combined, which is because these things are like, yeah, this, let's see, range 0 to that, right? One element less than that. So V combined is equal to uh, um, VACC max plus VCCW ACC max, and then we just need to find the max in the V combined. I hope that, at the end of this, the V combined value here is going to be 49 instead of 40 for this case here, because our money in the bank is always the same, but what's different is the V combined. Like, yeah, so it's a combined value of using something. Oh well, what is going on? Range. Oh, okay. Syntax error. There you go. Um, -1, 1. There you go. Syntax error. Something's wrong. What is it? Can only concatenate list to list. Why is that? Oh, okay. You can only concatenate list to list, not integer to list. So we have to make this into a list as well before we want to concatenate it, right? Um, yeah, what happens when we add these two lists up? Yeah, we probably shouldn't use, yeah, how about, Python element wise add element wise addition of two lists. What do people do? Um, operator add map. All right. So you're adding two lists, list comprehension, zip, list one, list two. Wow. You're using what list map at list one, list two. Use map with operator add or zip with the list comprehension. Timing comparison. 44 millisecond. Um, so the first one, so the map operator add is the fastest. You're telling me. Uh, list map add. Oh, you have to import the add operator. All right. I'm just gonna do it old school way. We're gonna just do uh, AV combined, right? So for k in range of that, I'm going to now v combined k is equal to this k plus this k, right? Do we initialize it? Yeah, we initialize it. So that is what we want to see here. So that's why we put a marker there. Invalid syntax, right? I think we forgot a colon right there. Computing, expecting 99, and MITB 45. So I hope the V combined max would be 44, hopefully. What? 54? Okay. 54 plus 45, that is 99. Yeah, okay. Okay. I mean, I can live with that. So you're going to give me 99? Yes. Okay, finally, I think we might have uh, a full solution here. Right, let's just click off that breakpoint, okay? And let's just continue with it. Oh, there's some error. Max arg is an empty sequence. What do you mean? Oh, sometimes vcombine is empty. Wow, I haven't thought about that. Which case is that? Is it the first case? It is, right. So with this very small array here, um, vcombine becomes empty because you know if the number of doors is if there's no doors, you don't really need to do anything like that, right? Right. So if there's like no doors, you don't need to do any of these. So and doors, um, we only calculate these things when we actually have doors. If we only have, if we don't have any doors, um, I mean, we just return the money in the bank, right? Right. If that's the case, um, then all values are money in the bank. But um, we're not going to do anything else if endorse is less than uh, less than 0. So calculate those, right? If endorse greater than 0. Mm, CCW, right? It has to work when at least you have one door. And if you don't have any doors, right? If you don't have any doors, um, if you don't have any doors, then you don't need to do anything, right? So else, if you don't have any doors, you just return money in the bank because you don't have doors, right? That's what I thought. Still, well, even for what? Even for um, two doors, actually, um, we took this, right? So there's going to be one door. And even for one door, right, even for one door, this is going to be like an empty array. Right, it's going to be like a problem. If it's just one door, if it's just one doors, right? If just one door or no doors, return MITB, money in the bank. So I'm going to do that and hopefully that's going to make more sense, right? 3, 10 minus 2, 8, 18, 4, what? 29. Wait, this one we expected 16 and it's returning 14. So that's another wrong result, right? Like for this one, we took, um, we knew that, we need this. And we know that, we need this and we can go all the way here. So this is going to be how much? 2, 1, so that's 3 on this side. And it's going to be 13 on the other side. So it's going to be 16 overall. Um, and we had 2 doors. So there's something wrong in this case. All right. So we're gonna take that. We're gonna pick that particular test case out and continue to fix our problem. Right. We're expecting 16, and it's the problem not in the case one, because case one is where we took out the -2 value, and that is correct. But it's case two where we have this. And we're going to first calculate the money in the bank, right? The money in the bank in this case is going to be 3 minus 2 is 4, it's 1, and then we have this 13, so it's going to be 14. So 14 is like the money in the bank. And we need to actually add, we still have 2 doors, so we need to um, add this V combined in that case. So I think the problem is with V combined uh, calculation here. So let's start with um, let's start with this. Yeah, put a breakpoint there. Okay, we need to. There we go. Okay, the money in the bank should be 14. That's correct. And we want to see why this didn't work, right? We're gonna walk through all of that. And do we still have like a drawing for this one? Let's keep a drawing for this case. We didn't have a drawing for this case. So let's create a drawing for this case as well. Mm, which case was it? I think it was, I don't know. I don't think, is it this case? Right, it is this case. Uh, and the greedy snake, well, didn't quite work. Um, we're going to basically reuse this part, okay? And then we're going to apply our latest algorithm to work on it. Now, let's remove the greedy snake stuff. Yeah, we're going to remove the greedy snake stuff and um, yep, right. So this is like that, and then Um, First, of course, um, we have shifted our problem into something like this, right? So yeah, it'll be a list like this, and then this is going to be our first element because we shifted the problem to make it easier for us. K equal to 0 there, and we indicated our correct solution with this black bracket here. And now we will look at, first of all, the num list 2. Starts from -2 and then all the way to 3. Yeah, it's the same list here. Uh, right, so this is like the shifted list, nums2, right? Nums2 is this list, and we start from there, and we have worked out correctly the uh, what is it like? Not that one. At this point, we have worked out our accumulative CW and CCW there. So let's just quickly recalculate those lists, all right? And let's match that with that. So we're gonna first draw our money in the bank with the orange color. So our money in the bank goes down here, and oops, and it goes all the way here to the number 8 here. Those are all our money in the bank. And in terms of doors, we're gonna again use purple to indicate these are the doors, right? So we have two doors. Um, Two doors. We're gonna have like 0, 1 is the door index. Uh, we can calculate our value of visiting those doors, opening these doors clockwise, V counterclockwise, right? And we're gonna have our V clockwise accumulative, V counterclockwise accumulative, and we're gonna have our V clockwise accumulative max. This one will have one less element, as well as the V counterclockwise accumulative max. And then finally, we will have our V combined. That is quite a lot of memories that we're storing, but it's still uh, ON instead of ON squared. So we can afford them. Now let's move these indices a little bit to the right. Yeah, and for this one here, so for the first door, the cost, let's take a look at this. Yeah, we only have one treasure chest in between these doors. So if we visit the first door clockwise, the cost, the value is 0. Um, this is of course -7 because we never want to visit the last door in the clockwise direction. This is -9, and this is, if we visit that from the opposite direction, is 2. So VCWACC cumulative. So if we visit from the clockwise direction, accumulatively, this is going to be 0, right? And then next one is -7. Yeah, let's just draw a line here to make sure we don't look at the wrong values. Uh, -7. So counterclockwise accumulated. So we accumulate from this direction here, and then it's going to be -7 there, right? So VCWAC max. So this is going to be it's just one value. It's down to one value. And this is going to be like the value of taking um, the first, taking the, the first door, which is this door, using counterclockwise direction, right? So the value of that is um, 0, right? Because cumulatively it's 0. And what is the value of that taking it counterclockwise? Um, it actually should be this value, right? Counterclockwise max. Mm, it should be 2, right? So combined, it should be 2. I'm thinking. Uh, yes, yes, I think so. So how did you calculate these two values? Can you show me? Because um, according to these, I think you should add uh, this value. You should shift, right? You should shift mm, AC max. Let's see, what was it? Actually, let's just take a look at the previous drawing. Right, here we have 5 doors, and accumulating them is a really gonna take all the attention you need. So the first door, this is like the first door uh, opening in the clockwise direction, and then the best you can do in the counterclockwise direction is to you know take that value, um, right? This number one here. What is this number one here? This number one here is supposedly the maximum value there, right? So let's compare it again. So it's the door number 0 here and door number 1. So the first element in this uh, um, the first element in, let's see, in this VCWACC max is as if you take the first door in the clockwise direction, or you don't take it, right? And then you're going to combine uh, it with the VCCWACC max of the second door, up to the second door, right? Of up to the second door, and you accumulate it. In our case, we still have 2 doors. So let's just stick with 2 doors and not jump steps, right? Um, because now, if you look, this value here, it's 0, right? Because if you take this, or if you not take this, the value is the same. And if you take in the counterclockwise direction, but if you take the last door here, you're actually going to get a net gain of 2. So the VCWAC max uh, um, is when, you know, um, right, the maximum value between this and 0. So uh, this and 0, it's still 0. But what about 1? Like, um, it's still gonna be 0, right? Because if we take the next door, it's gonna be -7. It's actually worse. So we're gonna stick with the previous maximum here. And what about VCCW ACC max? I mean, if we take the first door, if we take the last door, it's gonna be 2 here. And then naturally this one is at least 2, so it's 2. So now when we combine those, it's going to be this plus this, right, equals to this. We combine should be 2. And this one here, really, it doesn't matter. It doesn't matter. But let's just take a look at our previous calculations sheet and then take a look at this, right? So it's kind of like this value here. And the way we calculated it is like we take the VCWACC max value there and then we add it to the value here. This value is, if we take the max, yeah. So I think we're in good shape. We're in good shape, and we should see these list values, and then the V combined should only have, right. This is like all of these. They should have 2 values, 2 elements. It's only this one here that has 1 element. So maybe I got that wrong here because I think when we initialized all of these, yeah, we say, endorse -1. That is wrong. And that is really, really wrong here. It's only that these ones are still like with endorse, right? And it's only the last list that, this list is 1 element less than endorse. Right, but not these first 2. So for these first 2, we're still gonna do in range like that. And this is like endorse -1 down to that. And then, in this loop, we're gonna take maximum between 0, the current value, and the temp. Temp is what the previous maximum, right? Same here. This is like counterclockwise max, and it's a max between 0, VCC accum, and temp. Right. So right, right. And then when it comes to this V combined, it's definitely 1 value less, and no, and this is gonna be this plus 1, right? Because that's what we saw. That's what we saw, right, in our array. Because yeah, it's adding the kth element here and the k plus element there, and I think that's compatible actually in a way. 16. Yep. Now we have 16. So everything is a little bit now. Whoa. Now everything is a little bit uh, uh, more on the right path now. Let's just check. 3, 3, 10, 10, minus 2, 8, 18, 16, minus 1, 29, 99. Okay, so this now seems more correct. Um, But it's not the most elegant solution, but it's the only solution that I worked out anyway. So I humbly present this result and submit one more time to see if it works. Okay, works. The compiling took quite long. Um, this is correct. We still have a wrong answer somewhere. Okay. More test cases coming. So I think I did not generalize this well enough. That's why we keep getting wrong answers and we keep having to patch things. What is the answer that we're expecting for this one here? 14. Okay, 14. We were expecting 14, but we got 16. So how do we get 16? Um, we took out the fifth element, and then our money in the bank, it would be, there's nothing in the backward direction, so our money in the bank is going to be minus 7 plus 0 plus 2 plus 8, and it will be 3. So our money in the bank should be 3, and then we're going to just basically see what we're going to get traveling down these doors, right? It looks like we better do this. So that is a 3 with money in the bank right there. And then we're going to add a 9 to it. Hold on. Yeah, it's going to be a 3 here. It's going to be a 3 here. And it's going to be a 3 here. And then if we add another 9 to it, it should be 11. So this one should be 11. So we should actually output 14. Right, so that's something wrong in there, definitely. And we're gonna basically put a breakpoint in our right in here before step 2, right? And then we're gonna start with this. And then our money in the bank is 3, and that is correct. Because if we took 7 as snake, our snake heart, I'm taking some water. Right, if we take our minus 7 as our money in the bank, sorry, minus 7 as our heart, then our money in the bank is going to be the sum of all these numbers, and it's going to be 3. So our money in the bank calculation is correct. And then we're going to travel, we're going to travel down to our VCC and VC and VCC to build our values for our doors, right? Right. So we're going to put a breakpoint here at 127, and then we're going to move on, and then we're going to basically see what's in the list of our cumulative values there. 279. I think the 9 is the one that we should take, right? Well, accumulative. We want the accumulative version of it. Yeah, so the best we can do is to take this 9 here and add it to our 3, and we'll get 12 in total value. But somehow these calculations messed it up. So we're going to debug that, right? Yeah, we're going to debug this again with our hand calculation, and then we're going to, oops, um, yep, we're going to basically recalculate this again with hand. Now we can do this much quicker. Draw a circle, and then this -7 is our first index, right? So, and in total we have, I don't know how many indices, but this is going to be our first -7, 0, 2, 8, -5, -2, 5, 6, -2, right? That is that, and this is our snake heart, right? And snake heart, and our money in the bank is this part, which is MITB. It's 3, and then we're gonna draw our basically our doors. Door we have, like 3 doors: door 0, door 1, and door 2. And we have a treasure chest here, and its combined value is 11, right? So we can easily write down our 3 doors values. First is V CW, and then VCCW, and VCW ACC, VCW CCW ACC, and then VCW ACC max, and VCCW ACC max, and then lastly V combined. Okay, and because we have 3 doors, it'll be on 0, 1, and 2. For clockwise visiting doors, the first cost is just the cost. There's no treasure behind it, so -5. The second one is we get 11 in reward, -2 in cost, so 9 in total reward. That's the last door. Well, it's just the cost. Counterclockwise, the last door, again, reward 11, cost -2, so overall 9. And door number 1, just the cost. And door number 0, just the cost. Clockwise accumulated reward. The first one is what? Cumulative reward of taking the first door is -5. Cumulative reward of taking the first 2 doors is -5 and 9. It's going to be 4. And then also taking the last door, we're going to add a -2 to it, so it's going to be 2. Counterclockwise doing it, taking the last door, the value is 9. Taking the last 2 doors, the value is 9 minus 2, it's 7. Taking all 3 doors in counterclockwise, we're going to have to -5 to that. It's going to be 2 there. Right. So VCW ACC max, the first one is going to be 0, right? Because you can just not take any doors. For this one, we're gonna take 4 because we already have a positive value, and this one is still gonna be 4. VCCW ACC max, we're gonna look back from this direction. It's a very large, impressive number, and nothing's gonna beat that. So it's gonna be 3 nines right here. And V combined, it has only 2 elements, and we're gonna add that and that, and then this is gonna be 9, and we're gonna add that and that. This is gonna be 4 plus 9. It's gonna be 13. Right. So we actually created a plus 13 combined value, but is it true though? Because this means what this means. This means that we're gonna take a door 0 and door 1. Um, take door 0 and door 1 uh, uh, um, in the positive direction, and uh, we'll get a reward of that much. And then what? You're gonna take the last door as well. You're gonna take the last door from there as well, and you're trying to claim this reward again. Well, you seem to have claimed this reward twice. Yeah, that's a problem. You claim this reward twice. You think you can have a combined value of 13, but actually you took these 2 rewards twice, and that is not right. That's simply not right. You actually need to minus 11 to that because you took that reward twice, so you actually only got 2. So, anyways, we found our problem. The problem is that you know um, the problem is this. Um, if we actually allow, uh, for example, ourselves to take the first 2 doors on the left and take the last door on the right, it seems like they don't overlap. But then actually, you know, the reward in between, you have taken this twice. You took this once, but you've taken this twice. And that is wrong. So, how do we fix this? The way to fix this is this. Like, if you actually took the first 2 doors using the forward opening, uh, using forward door opening, then you can no longer open the door here anymore. Um, you can only do it like this, right? You can only do it like we open this one, the first one on the left, and we're gonna open the third one on the right. So then we're gonna take the rewards just once each, right? Um, I mean, you can still try to open the store either, from the left or from the right or like from the right, but there's no additional reward anymore because you're gonna have to be faced with what? You're gonna have to be faced with an empty loot, empty treasure chest once you open that door. So when we accumulate this, right? When we're adding these things up together, you need to make sure that you don't really add them like this. So what do we do? Well, the right way to calculate, I mean, this 0, it means like the maximum value you can get if you just maximally open this door on the clockwise direction, right? Um, then, if that's the case, there's there's no it's 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 making no sense to open more doors than the last door on the clockwise direction. So you're actually adding this to this, right? And you're gonna get a answer of 9 here. Because if you actually open both of them, open both the first and the second one, then you cannot open any more doors anymore. So it's gonna be just adding a 0 to it, and well, you're gonna get a 4 here, right? Maximally. That's that. So yeah, it's shifted like actually twice, right? So it is very crucial that when you create this list, um, for this one, you have to, this list has to shift 2 positions, uh, uh, and be patched with a 0 at the end. Right. So that's what you do here. So when you create the second list here, let's just stop it. Um, so when we created um, this VCCWACC max, right, when you created this, you know, I mean this list has to be shifted by 2 indices and be patched with a 0 at the end to make it work. It's a really complicated way of doing it, but anyway, yeah. So it's gonna be k plus 2 here. Um, right. So we're gonna patch a VCCWACC max um, equals right equals itself, you know, with a patch, patch a 0 at the end of this list, and then we can do a k plus 2 here, and then it's gonna work. Yep, I think so. Right, now we have 14. All right, that's a fix of our rule here. Let's see all our solutions. 310 minus 2, 8, 18, 14, minus 1, 29, 99, 14. Okay, that seems correct. Let's submit it. Hopefully it'll work this time, but no guarantees. Let's just take these excess diagnostic signals out. Uh, run sample cases, it worked. Submit. Again, there's a wrong answer. But hey, isn't this like the case that we worked on before? I mean, it looks like a test case that we had before. This case, right? 05A minus 99 minus 72. Expecting, yeah, we had that. Expecting 16. Oh, okay. So this one became problematic now. Interesting. That's interesting. So, right, we were expecting 14, 16, and we got 14. I'm pretty sure that, we took the minus 2 there, and our money in the bank is 1 here, and plus the 13 here. Money in the bank is just 14. Uh, but then um, money in the bank is 14, but we had, right, then there's the additional value of going to the left this much, right? So there's an added value of this much, and somehow this didn't reflect it. So again, we need to go into debugging. We're going to uh, put a put something here right in front of step 2. We're going to just debug it. Whoops. All right, restart the kernel. Kernel restarting. Starting the debugger, and we're going to place our breakpoint right at the beginning of step 2, because the first thing we want to check is whether the money in the bank is calculated correctly. It should be 14, and it is. So so now we can just travel further down to see if our calculation for these arrays are correct. We're going to pause our let's see, accumulation. Yeah, we're going to pause our breakpoint here and then move on and see if these VCC accumulated arrays were correct. But in order to do that, we still have to travel back to our original example there. I think it was this example, right? Was it? Our money in the bank is what? Money in the bank is uh, 14, right? Yeah, it is this example. So I'm just verifying it. We're, we're dealing with this example repeatedly, right? -2 all the way to 3. Yeah, -2 all the way to, so it is this example. And let's check if and we have 2 doors. Let's check if the VCW is correct. Our VCW is -7 and 0. Yep. And VCCW, it's -9 and 2. Yep. And VCW ACC, VCW ACC, -7, 2. Oh, that's VCCW ACC. So VCW ACC is this one here. 0 -7. Yep, and then the other is -7, 2. It's also correct. The next one would be VCW AC max. It should be 0, 0. VCW AC, VCW. Oh, I haven't calculated them yet. Let's calculate them, right? Let's put them here. Another breaker, another breakpoint. Turn. Right. Another one just right here. Step forward. And let's check VCW ACC max. Is it 0, 0? Yep, it is 0, 0. What about VCCW ACC max? Is it 2, 2? Well, for me, because I think with the new addition, I think I'm going to right shift it, right? So it's going to be shifted. Yeah, this is no longer true because we have um, shifted it twice, right? So what is true is that now this thing has been uh, 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 we need to shift this twice, right? Um, so this one should be connected with this to and produce this. So this will be 0, right? And is that what you're talking about, right? And then yeah, and then that's it. There's no value here. But if it's combined with a 0, that means okay for the doors. What does this mean? This means we're taking the first door in a clockwise direction. Is that right? Yeah, we're taking the first door in the clockwise direction, and we're not taking we're not taking the second door. We're not taking any doors in the in the counterclockwise direction. That seems to be a pretty bad idea because we are missing out on something. We're missing out on, the possibility of actually, this and that, and that should be 2, right? Because this means that we don't do anything. We don't do anything in the clockwise direction, and we actually take the door here um, on the counterclockwise direction. So yeah, we should get this 2 here. So I think the expression there is still like flawed. Um, Let me just again fix this. I'm gonna put this here, right? And I think actually this one now actually has 2 values. And the first value is going to be this, and the second value is going to be with this, right? You add them up, and then you go to this value here. So that being said, we're going to patch. Um, we're going to shift. We're going to kind of like augment this um, to the left, and then augment this to the right, and then we shift 2 values to get this value here. Yeah, it's pretty weird add, but I'm gonna take it as a fact. So let me just correct that there as well. Um, so here we actually, instead of adding them like this, um, so this actually should also be combined, should also have 3 values. Shift to positions and be patched with a 0 at the end. And similarly, this one here should be this list has to um, be patched with a 0 at the beginning, right? So what do I mean by that? It means we're going to do this, and we're going to do this, and this, and this, right? So this is going to be a 9. This is going to be a 9 here, and we're going to patch a 0 here to the end. We're going to add it like this, and this is going to be a 4, right? Um, so how do we do this? So during the generation of this array, um, we're gonna say, hey, we're gonna basically take these three values, and we're gonna take these three values, okay, and then we're gonna arrive at these three values. So instead of like shift it, let's say pop the last element and be patched, right, pop the last element and be patched with a 0 at the end. This list has to pop the first element and be patched with a 0 at the beginning. Right. So let's do a pop. Python pop. Right. Python pop, and by default, it's going to pop the last index. Default is the last one. Right. So let's do it. First of all, we're going to basically initialize this one with the same length. Right. And we're going to basically, for this one here, after, after its creation, we need to pop the first element and patch with a 0 at the beginning. What that means, wait, I think this is like actually the first. This is going to be popping the last element. And let me patch with a 0 at the beginning. Right, okay. So this one here is add a 0 at the beginning and then pop the last, right? Pop last, add a 0 at the beginning. Got it. Pop the last. So VCW AC C max equals to a 0 at the beginning, and then we're gonna pop the last element, right? Right, and this one here is um, patch 0 at the end. Pop the first element and patch 0 at the end. So we're gonna do pop 0. So now this one here, 0 to endorse, is gonna be just k plus k. right? Because now it's element-wise matched. Yep. I hope we're correct now. What is it? Oh, we can only concatenate lists to lists. So when you're trying to add them, wait, after the pop, it's still a list, right? Isn't it? Um, Pop the last element. You can only concatenate lists. I mean, what is this, right? I mean, we are still adding lists to lists. For example, let's see what is uh, 0, 1, right? Test dot pop minus 1. What do we get? Oh, no shit. This become what? An integer after the pop. I didn't want that. I wanted, you know, maybe we don't use pop because pop is going to reduce that sometimes into an integer. So if we want to just pop the last element, we're going to do the first two, I guess uh, minus one, right, and one. Pop the last element. That's how you do it without a pop. But this has to have at least maybe two elements in it, because if we have more than two doors, we can do that. And the other one here is instead of pop 0, we just say we're going to do 1 till the end, right? So hopefully that is not going to work. Wait, what is this? Listenesses must be integers or slices, not tuple. Oh, a syntax error. Right, I've been coding this for like, I don't know, 5, 6 hours, so experiencing a little bit of a numb. But hey, we solved this case here. I think we can hopefully get all the cases to a pass now. 310 minus 2, 8, 18, 16 minus 1, 29, 99, 14. Yep. This is it. But we did go through a lot of changes and test cases. So this kind of problem really got me. Huh? Oh wow, wrong answer. Even for the first case. Oh, okay. We have included, too many answers for the main function. So now this is correct. Test cases, correct. Submission, judging, finally accepted. Wow, what a relief, guys. I finally got accepted. Let's run it again, submit it again to see if performance-wise it's better. Actually, it's not. So this is still below average. Wow. Let's try it again. Right, it's still pretty slow. So our code, although I've worked a full day on it, I mean it's literally taking me one day to work on this problem. But still, I don't get to be an average solution. I guess I'm not really good at this. Um, and okay, I'm gonna take a look at the solution here. The rating is not really high, huh? So solution is about what a primer on Kadani's algorithm. How many approaches do we have here? Next array, uh, prefix sums and monoq, um, complexity O n and O n, Kadani's with sign variant O n and O 1. That's pretty good. Kadani's mean variant O n and O 1. Wow. People are saying this explanation is bad. Wow. Okay. People are saying that this solution article is bad, but let's try to see if I can get something out of it. Okay. Explaining of Kadani's algorithm, and then there's this next array algorithm, um, O n and O n. We have this prefix sums and monoq. Uh, uh, that's not really good. Let's take a look at the Kadani's sign variant. O n and O 1. This is pretty good. Let's see. Wow, this is so elegant. Let me actually try that and see how fast this can get. Okay. Wow, this beats our code immediately, and it's so elegant. So I think I am definitely missing something, really good in the Kadani's algorithm, um, and we didn't really get, the full benefit of it. So let's read this approach 3 and see if we can get it. Okay, as an approach 1, subarrays of circular arrays can be classified as either uh, one interval subarrays or two interval subarrays. What are those? Let's take a look. Approach 1, two interval, one interval. Okay, let's read this. Subarrays of circular arrays can be classified as a one interval subarray or two interval subarrays, depending on how many intervals of the fixed size buffer A are required to represent them. For example, this one from 0 to 6 is the underlying buffer of our circular array. We could represent this subarray 2, 3, 4 as one interval 2 to 4. Yep. But we would represent the subarray, 5601 as two intervals 5, 6, and 01. Right. Right. Okay. Because the second one has reached the end, and then it has a deflection back to the beginning. So that's why we need two intervals. Using canonical algorithm, we know how to get the maximum of one interval subarrays. Yep. So it only remains to consider the two interval subarrays. Hmm. Right. That's a pretty simple classification here. So let's go to the Kadani's sign variant algorithm. So write one interval subarray, two interval subarray, using the algorithm Kadani for finding the maximum sub of non-empty subarrays. The answer for one interval subarray is Kadani A. Yep. Now let n equal to a dot length for a two interval subarray like a0 till ai plus aj till a minus 1. So this one reached the end, right? And this one starts from the beginning. We can write this as um, sigma k equal to 0 to n minus 1 ak. Oh, minus what's in between. Okay, okay. You can make it to be like a difference between the full array and then just one another array. Okay, so you're mirroring it back into a one interval subarray. So let B be the array A with each element multiplied by -1, right? So it's going to be the opposite array of that. And the answer for two subarrays is um, sum A plus Kadani B. Right, it's true. Except this isn't quite true. Okay, as if the subarray of B we choose is the entire array. The resulting two interval array would be empty. We can remedy this problem by doing Kadani twice. Once on B with the first element removed, and then once on B with the last element removed. Okay, so answer 2 is the Kadani is the sum of A plus Kadani minus AI for that and that. So we do have another loop in here. We do have another loop in here. Okay, but it's okay. It's still ON. We have just a few numbers of for loops here, and it does not scale with n. Uh, and then we return the maximum of answer 1, answer 2, and answer 3. What is iter A? What is iter A? Python, iter A, iter function. What does the iter function do? The function returns an iterator for the given argument. Okay. Okay, so it iterates it once at a time. Mm, It iterates A, so it's only taking. What is gen? Gen is maximum non-empty subarray. Well, I think this Kadani's algorithm is really powerful here. It's so elegant, and according to your description here, you kind of like broke down the problem into either one interval array or two interval subarray. And for the two interval subarray, you just apply another trick. Use like a mirror trick, kind of like make it to be the difference between a total array and then and another subarray with the minus sign in front. And you could express it in like this form. Uh, and then you did it like this, right? Pretty much, um, pretty much. So, so this is an algorithm that I think really gets me, and I haven't learned the essence of this. I believe of the Kadani's algorithm. We implemented one version of it, but just by the look of it, this is much more elegant than what we have. Um, So I guess this solution was able to just come up with Skadani's algorithm um, elegantly to come up with these solutions, right? Right. Okay. I think I'm gonna spend um, some time on my own to learn this Kadani's algorithm and then try to explain this in the next episode. Okay. Um, this is a really tough problem again for me. It took me a day, and I just barely got past with the very lengthy solution and very inefficient. Right. Let's take a look at some of the posts where people have solutions, right? And they have created elegant Python code and Java code and C++ code in very elegant ways. Well, that's pretty cool. I might take a look later on some of these, uh, you know, user posts. Clean and concise Python solution here. DQ solution. Wow. Okay. You know, this is one of the days where I just really struggled through the code, but yep, we managed it. So that wraps up today's video, guys. Um, for the summary, I guess what I can say is, don't be too stubborn. Like I've been too stubborn today, and I'm trying to, work out this solution and I just dive deep and deep and into it. And even though it worked, it took like 10 hours. Yeah, it took 10 hours to finally get it done. So I think this is like a negative experience or like a lesson that you guys probably should try to avoid. I mean, I still learned something, um, but the time invested into this for this problem, um, it's kind of like not worth it. You're not trying to. You don't want, at the end of the day, we just want to solve these problems in an efficient way. We're not going to try to get at the bottom of it, right? So this is like a negative experience. So I'm not going to talk about the details of the implementation that I used today because it's a rabbit hole that I barely got out. And I don't think I can, make this into a cleaner form even within one more day or so. So um, please just remember this lesson and try not to spend more than 2 or 3 hours at one problem and maybe just jump right into the solution, learn the most efficient code and try to understand how that works and build that into your memory. Um, and then just move on, right? Nobody gets everything in the first time by their own. Um, so nobody is that powerful. Um, so it's okay to just sometimes sit back and take a look at the solution. So that is actually what I'm going to do in the next videos. I'm going to set like a hard time limit on it, maybe 2 hours, maybe 3 hours, and at those time limit marks, I'm just going to um, stop trying and then looking at the solution, trying to understand the solution, and just share what I have learned from the solution, and then just implement the code. Um, Try to implement the code by not looking at the exact code solution, and then just implement one of the most efficient solutions by following their description and then understanding them. So that is what I'm going to do next. Um, so thank you guys. That wraps up today's video. I'll see you tomorrow.